All right. Hi, everyone. Thank you for being here. It's my pleasure to introduce the workshop on integrated perception, planning, and control for physically and contextually safe robot autonomy. I'm co-organizing. My name is Autonomy. I'm at UC San Diego, and I'm co-organizing this workshop together with Omur Arslan, Rafael Matthias, Jin Kim, and Mehmet Gogar. So we'll start with a brief overview of the workshop objectives and the schedule, and then we'll move on to the main program. So let me first tell you a bit about our workshop. So we've seen a lot of progress in motion planning, in control, in scene understanding. We have a lot of neural network techniques for object detection, surface mapping recently, a lot of progress in manipulation. But the motivation for this workshop was that a lot of these techniques tend to be disconnected. So we first build a map and we freeze it during motion planning. We identify objects and shapes, and then we don't never change them during manipulation. So the objective of this workshop is to investigate techniques that couple perception, planning, and control in a much closer loop where uncertainty in perception is taken into account as we're doing motion planning or control, or vice versa, motion planning and control are used to improve perception and actively observe the environment. So the topics of interest in this workshop include perception and learning for planning and control, perception-aware planning and control, active and interactive perception, semantic perception and semantic planning, affordance-based planning and control, uncertainty-aware planning, contextual risk and safety assessment, and contextually safe human-robot interaction. So some of these topics are related to active SLAM. So you can, one of the places where active perception has been studied for some time is the area of active SLAM, where we're trying to plan the motion of our robots to perceive the environment. But here things are still very much focused on how to use planning to improve perception, but not how to use perception to improve planning. We've seen the opposite as well, where, for example, we use perception to improve planning or control. For example, perception-aware model predictive control enables flow routers to do more robust flight and reduce localization uncertainty. But really what we're aiming for in this workshop, it should be better. All right. So, but really, this paper from 2017 is kind of an inspiration for the objective of the workshop, is the idea of leveraging action in perception and perception in action. So with this in mind, we have an exciting lineup of speakers that work on several areas of robotics, including navigation and manipulation. And they have done work that integrates perception, planning, and control in various aspects. We have Kostas, Alexis, Effie, Psomopoulou, Georgia, Chalvatzaki, Choi, Coline, Devin, Hyeonbeom Lee, Roberto, Martin, Peter Karkus, and Rohan, Chandra. These will be our speakers for the day. And I will have Rafael introduce the schedule for the rest of the workshop, and then we'll proceed to the first speaker. Thank you.
Yeah, hello everyone. I am Rafael. So we have a schedule online that you can access if you scan that QR code or by accessing that URL. You should be able to see all the talks, the abstracts, but also we will have some exciting posters out there, and you can access the workshop papers directly from the website. So as you go out later on to see those posters and you're interested in the papers, you can access them directly from the schedule. So I will give a quick overview of that schedule. So we have the morning session. We will start with two exciting talks. from Kostas and Effie. Then there will be the poster session a little before the coffee break. So we are inviting you to go out there and chat with our poster presenters and see the exciting work that they will present. Then we will have the coffee break, and then we will come back with 2 more exciting talks, followed by a discussion panel that we will discuss the robot perception for navigation and manipulation. After that, we will have the afternoon session. So again, we will start with 2 talks, and then we will have the poster session on perception-aware robot navigation and manipulation, followed by coffee break. Then we'll come back for 3 more presentations, and we will have the afternoon panel discussion on perception-aware robot navigation and manipulation. And finally, we'll close the workshop day also by announcing the Best Poster Award. We will be announcing the Best Poster Award at the end of the workshop. So, as I said, we have some exciting poster sessions. This is the morning session. You can access the titles and the author details on the website. And then this is the afternoon one. So I will invite now Kostas, Alexis, to join us and give the talk on resilient autonomy in perceptually degraded environments.
All right, thanks a lot first of all for the invitation for the organizers. And I'll be talking today about resilient autonomy in perceptually degraded environments. And in particular, Zoom is trying to take ownership of screen, okay? In particular, I'll be talking for 2 subsets of method. The first, and so let the video play. The first will be about just resilient perception without any coupling to perception and control. And the second will be about correlation between perception and control for navigation by means of using a deep learned navigation method that accounts for uncertainty in the, for example, part of the localization problem. Now, to motivate my talk, and it's the first talk of the day, then it makes sense to look at something that is relatively cool. I show some results from previous work of the lab and in collaboration with the lab alongside in the framework that we did in the Data Subterranean Challenge, and also in the framework of method of work that relates to, in some form of fashion, exploration, mapping, inspection, navigation in highly confined environments. So that's the overarching idea behind all the set of videos that you see here. Now, the discussion that I want to bring is how we facilitate resilience and resilient autonomy in challenging conditions. And if we're to think specifically in perceptually degraded environments, how we facilitate resilience across perception and control for navigation in order to make sure that our robots navigate safely in environments that might be, for example, dark, with obscurance such as smoke or dust, self-similar geometrically. So for one reason or the other, our localization might fail. And the main claim, I would say, is that we need 2 things. We need sensorial redundancy or multimodality. So not multiple sensors of the same type, but actually sensors that provide distinct signals that fail in distinct conditions. That's number 1. And the second thing we need is resourcefulness in the algorithmic architecture, both for perception to exploit these modalities in diverse ways to make sure that we have, for example, a good localization estimate. And second, in control for navigation, the key idea is that the traditional scheme we are following, that we have an estimate and then we deploy a controller that trusts this estimate, maybe with some uncertainty, alone is always prone to fail. And we've had a lot of experience that we actually have failed in several field tests, most often than not because localization has been a problem. So in this general scheme of autonomy that you see in this block diagram, the focus of the day-to-day will be primarily first on resilient perception, and then I will focus on the lower right part about low-level control that accounts for localization uncertainty. So let me then go to the first part about perceptually-degraded slum, for example, and let's consider an environment that a lot of these features of degradation happen together, so there is no external support, so let's say no GPS to speak practically. It's dark, it's self-similar geometrical, like a self-similar panel, and then it may be or may not be filled with obscurance. And the core idea is that all these conditions don't happen simultaneously, all at the same time, but they happen at distinct conditions. Maybe 2 of them happen at the same time, but one, for example, doesn't happen. And as you understand, if it's self-similar, LiDAR localization is bound to fail. If it is visually weak texture-wise, then visual localization is bound to fail. If it's filled with smoke or dust or something like this, then both these type of modalities are, to the extent it gets dense, bound to fail. And you're going to see some results with even worse conditions than what you see in this video. So back in 2018, when we were preparing our team for the data sectorial challenge, we developed what I would call a loosely coupled approach or multimodal SLAM that essentially exploited visual inertial odometry and thermal inertial odometry to fit signals into LiDAR registration. And based on some checks on the d-optimality metric of the evolving covariance of the visual odometry, and based on checks on the eigenvalues of the underlying Hessian as we did LiDAR optimization, localization, and mapping, we're able to detect if any of the two modalities fails in a certain condition, and accordingly trust the other under the assumption that either vision or thermal vision or LiDAR will survive at any given time, at least one of the three, right? So here, for example, we're in a set similar tunnel, and it is obvious that LiDAR is bound to fail. And at this condition, of course, detecting it through a metric I'm going to show later, we're able to make sure that the expected degrees of freedom are propagated through the estimation of visual inertial odometry. So that's straightforward. So I move forward to the next step. Now, the moment I mentioned this loosely coupled approach, as you understand, there is a person, an engineer, a researcher who thresholds everything and made this architecture that somehow knows which modality works at any given time. Because the natural, more obvious step to take is to put all the modalities in a factor graph and try to optimize together. So in this condition, let's assume that we have generally two types of modalities, LiDAR, which is, for example, the more accurate sensor in these conditions of interest, but that's not a generic statement, but in these conditions of confined structured environments, to the extent that they're not so similar and to the extent that they're not field of assurance, it tends to be more accurate than other sensors, more often than not. And then we have, for example, any other source of photometry, for example, from vision, from thermal vision, and so on. Now we put these things together alongside IMD factors, so just the inertial integrated factor, and then we solve a combined optimization problem that puts all the constraints together. Now, as we put all the constraints together, I will already say that there is a limitation. As we solve this quadratic optimization problem in a sliding window, let's consider, for example, the fixed like estimation formulation. This means that if an odometer, if a certain source, for example, LiDAR in a certain similar tunnel has a wrong estimation of the length, let's say, of the tunnel, it will still be there that it adds constraints that are actually erroneous. And the trick will be that for this particular degree of freedom, we will be inflating the covariance to a level that essentially does not play a significant role into the combined optimization problem. So this is still, I would say, it contains an error. I'll discuss another approach afterwards that solves this error, but I'm just describing incrementally as it was developed in the framework of our research. Nonetheless, to the extent we detect this degeneracy correctly, and as mentioned, as we solve the LiDAR optimization problem, we have the underlying Hessian, we threshold eigenvalues on this problem, and we find which degrees of freedom are degenerate. And we also threshold the value of the d-optimality metric, which indicates the surface of the covariance bubble of an odometry method. And we threshold this also. So by that, we know if LiDAR or our, for example, visual inertial odometry is failing for a particular degree of freedom at any given time. And we make sure we inflate the covariance of degrees of freedom of each that are failing. And the underlying idea, again, I highlight, is that the two modalities are not failing simultaneously for the same degree of freedom. Now, if we put this together in a test, this is here a electric robot animal in a test in Switzerland, and together with our colleagues from ETH, and it's going down a similar tunnel of a mine, and then it's supposed to come back, right? And the moment it comes back, it is natural, it's going to misestimate this part of the map, and it's going to have a failure in its localization. And what you see on the right, which is the revised method, we see actually correctly shaped tunnel. And likewise, if we, for example, here delete data from LiDAR, both methods, of course, are essentially able to survive both the previous method and the new method, because here we have a clear indication about which modality is failing.
Sorry, the screen is not shared.
The screen is not sharing it.
Yeah, sorry.
Is it fixed? Or so we think that is. But now it should be shared. Yes. All right. Now, I make a particular post to discuss about thermal inertial navigation because I have promised to speak about obscurance, so dust and smoke, but none of the work so far, LiDAR alone or vision, will actually make it work. So back in 2019, we did some work that allowed us to navigate in this environment that are filled with smoke. And pretty much this involved also a fixed lag estimation problem on which we had key points coming from thermal vision. The key points from thermal vision were all exploiting the 16-bit frame of thermal vision because the gradients are much weaker compared to traditional vision, for example, in these featureful environments. And the optimization problem is much like what we would expect. Instead of a photometric error, we will have what we will call a radiometric error. from thermal vision, we do a coarse pyramid from a higher level to make associations all the way to the lower fine resolution level of the pyramid to make sure we speed up. And we solve a combined optimization problem of constraints coming from the key points, so projection errors, and also constraints coming from the IMU. So just the IMU information matrices weighting essentially the propagation of the IMU. And this, back in the day, allowed us to navigate some environments that contain obscurance to the extent, and that's a difficult assumption in many cases, to the extent there is thermal gradient in this environment. So here, for example, it worked great because there is thermal gradient because we're building different materials, so different dissipative properties, and so on and so forth. But it's not necessary, for example, to work in a natural cave where you have the same rock formation in pretty much stable temperature conditions. So with all of that, I try to build up the necessity for a method that is more principled and gives us three capabilities. First, it doesn't assume that we know which modality has failed with a heuristic function that we develop and hand-tune at any given time, number one. Number two, it allows to integrate modalities that truly don't fail in conditions of obscurance, much more dense than what you saw in the beginning of this work. And third, it allows to flexibly add modalities in the same simplicity as the previous loosely coupled approaches. So to that end, this is a very recent work that tightly couples, now changing the terminology, tightly couples LiDAR and radar sensors alongside IMU. And what's the key approach? The key approach is that every feature from LiDAR, every corner that you extract, every surface part that you extract from LiDAR is added as a constraint into your factor graph, which you build over time and you're optimizing over a sliding line. Radar is adding constraints based on exploiting velocity Doppler information, which in fact allows us pretty accurate estimation of velocity, which is indeed important because this is not a competing estimate compared to the XYZ localization, for example, that LiDAR will be giving you alongside this path. And we also fit IMU constraints, of course, in the problem. Now, this means that if LiDAR is degenerate in one condition, it will be reflected on its features without us having to tune any heuristic function to that end. So for that, I give also more of a formulation. We have essentially all the error metrics coming from each modality, and all of them are added essentially as constraints into the optimization problem. So IMU, LiDAR, radar, and so on and so forth. We fit everything on board, collecting data with a system that has an also OS0 LiDAR, a radar from Texas Instruments, and again 100 IMU. And the result I'm going to play the video, but I'd like to focus in a second, is this. We have an area that is filled with dense smoke. You see the image of the robot that you can barely see the flying machine there. The LiDAR can only see up to 2.5 kilometers away simply because it's degraded with smoke. And well, I'm promising you that the technology works, right? So then I'll just play the video directly. So here's the system. It's taken off and enters this obscurant field, so smoke-filled environment of our university. And at this point, the only solution that survives, you saw the other parts in the previous image, is the LiDAR radar inertial solution. The radar inertial solution survives on its own, but it drifts more easily over time. And the LiDAR constrains part of the degrees of freedom, and therefore ensures that eventually we will have an accurate estimation or a reasonably accurate estimation of this corridor. So you should expect a straight corridor, and you roughly see a straight corridor, less than what you would see in an environment that there's no obscurance, where LiDAR will work like a charm out of the box, but much better, of course, compared to just working with LiDAR alone, for example, that would have failed in the first 2 or 3 minutes. 2 or 3 meters of navigation. And the system eventually will exit the obscurance field area, and soon it will be able to be in a clean area without obscurance, and therefore LiDAR naturally will work just fine. And I'll have more of the results, maybe if necessary, we'll have them online. But eventually, when it comes back after it exits the smoke, you can see it comes back to the correct spot where it started, which indicates that the estimation of the scale of this part of the tunnel, of the corridor, is correct, because when it's estimated in the clean environment, then naturally it makes a good localization. So for that, I'm gonna just let it play for 1 more second, or speed it up. No, it doesn't want to speed up. So I'm gonna show my image. So when it exits, it went to the clean area, and then it came back exactly to the correct point of the scene. And likewise, the same capability can be developed in a self-similar tunnel. This is a very cool tunnel that we found in Berlin, which is a bicycle tunnel. It's just straight over several kilometers along some very small curves. So here we are in 500 meters approximately. That's just continuously straight, right? So LiDAR is bound to fail. And you see the 3 estimates. Essentially, the LiDAR one is already starting to fail. You see it on the left. And then you see LiDAR and the combined LiDAR and radar going together. And eventually the LiDAR radar is more accurate compared to radar alone. But radar alone indeed survives also in this case where LiDAR already drifts far away from the map of the tunnel. And this also goes for a long path because it's roughly 500 meters. But I promised to discuss not only resilient perception alone, but the correlation with navigation. So when we finished the Double Subterranean Challenge several years ago now, the main conclusion we had is that both us and also most teams failed several conditions because their odometry or their map had failed. And it had failed to the level that it stopped collision avoidance, right, to be safe. So from then we departed with trajectory to develop a methodology for navigation that does not actually have a map of the environment purely for the purpose of collision avoidance. It is to be interleaved with traditional motion planning that ensures collision avoidance by exploiting a map. So we will still doing collision avoidance on our volumetric maps based on SLAM. But when we command the path, we don't now have a methodology that blindly assumes that this is actually collision-free. We have a methodology that revisits the idea if this is collision-free. And to that end, it exploits a depth image, an instantaneous depth image. It exploits the partial state, which means the state of the robot without the position. So it exploits linear velocity estimate, rolling pitch, and angular yaw rate. The uncertainty over this state, to which we sample through the use of uncertainty transfer. And we also focus on the epistemic uncertainty of the neural network, especially because during simulation training, we are not modeling actually all the errors, shadowing, and so on support present in the depth camera. So in this neural network, you see on the upper part, we are using the depth image, and we are using also the uncertainty partial estimate. We feed this through what we call collision prediction network, which is a deep ensemble to focus on epistemic uncertainty, and we spit out which of possible motion primitives is the safest to get to the heading direction by means of a goal vector calculated from our original SLAM solution, which might drift during the execution of this short horizon path, because this is a navigation task roughly for, let's say, 200 milliseconds or 100 milliseconds every time, right? So again, we focus on both epistemic and aleatoric uncertainty. Aleatoric by focusing on the covariance of the partial state to which we sample sigma points. And then because we're doing parallel evaluation in the GPU, this is very fast to do inference. And epistemic uncertainty to the deep ensemble to account for the noise in the, or for the epistemic uncertainty of the neural network, primarily driven from the noise on the depth image data. And the result that you see here is an instance of what I described. And time-wise, we are okay. Good. The robot will start. It doesn't have an estimate, it doesn't know the map, it doesn't have an estimate of position, and it has to go to the heading direction while avoiding, of course, all obstacles. And this is what it is doing in this particular iteration that you see here. All right. So with that, I want to close the main part of the talk that I wanted to give first and highlight again the basic conclusions from this. And I'll have a small part at the end about just feeding everything alongside planning to a more complete mission. But the key conclusions that I have so far is, first of all, the importance of investing in robust localization methods and mapping against conditions of perceptual degradation. And to that end, the first conclusion was the necessity of feeding multimodal sensors because we need to have signal information, right? We cannot just have signal that is, essentially so high noise at any given time, despite conditions of self-similarity, obscurance, and so on and so forth. The second was to try to optimize this combined multimodal SLAM problem in a principled manner without having a human tuning and heuristic functions about which modality works well at any given time. And this is something that we're still working further in our group. And the third key message is that we need to eliminate the assumption that we do SLAM, we build a map, then we make a volumetric presentation of the map. We plan collision-free paths in this map, and then the low-level controller is just bound to execute them. So here we are having a high update rate control, that's roughly 10 Hz on the TX2, actually then it's a very nature of the machine. And then it replaces essentially your traditional position control that you'll be running on the system by just following the command path. Now, we do have also work that tries to bring all these things together. And let's take, for example, the case of exploration path planning or inspection path planning, where we would be using traditional data structures such as graphs to span the volumetrically mapped part of the environment through our map solution. Here, we do the traditional mistake everybody does of freezing the map, or almost everybody, but we also do this at this point. We sample a dense graph in this frozen map, locally, not globally, because this map might be kilometers in size. And we optimize some utility function, for example, for exploration, for inspection, and so on and so forth. We also account for constraints such as traversability analysis by telling, the change of the voxel size on the terrain. If we have a legged robot, we deploy these things in the data subterranean challenge to also account for traversability for animal and so on and so forth. And you see three results here. In order of time, the bottom right is the oldest, then the next is animal, and then the flying one inside the ballast tank. The first two are inside some underground mine. The other one is inside the vessel, on the sides of the vessel, for the ballast tanks that are typically filled with water for stability of the vessel during sailing. And the planner essentially exploits the localization and mapping solution in order to execute this exploration part. Whereas on the right, after it does exploration, it takes the map and then calculates directly a full inspection path. I will conclude in saying that I have more details of all that in my keynote that starts from the data subterranean challenge and extends into recent work, and emphasize the following in the interest of time of the workshop, that we have open source a lot of the work that I explained in this talk, or we're open sourcing more. But I think the two important things that I believe are relevant to the discussion of this workshop is the first two. It's Oracle, which is the deep learned navigation policy that accounts for uncertainty, as mentioned, and also has an extra layer that I did not present, which we call attentive Oracle, and allows the system to navigate to an area while simultaneously attending towards areas of interest. This, for example, could be your features from your SLAM or something else that you want to attend to do combined collision navigation with implicit information sampling. And second, a simulator from one of my PhD candidates, also, who is also here at IROS. He is also contributed in the first work, which is based on ESRG and allows you to, we have developed the simulation models for flying robots, quadrupeds, and so on and so forth, and allows you to do millions of robots simultaneously running for training purposes, and also simulate, for example, depth cameras. Then you simulate less number of robots, but still with quite high efficiency. And to that end, I just also highlight the third piece of open source work that I wanted to potentially consider, GB Planner, which is the exploration planner that allows to guide all the robots in the Chalvatzaki. And all the methods are open source, and we're happy to get any input if you like it. And lastly, I want to say is that we're hiring 10 people, PhDs and postdocs across projects. So if you have any interest, please let me know. Thank you.
Thank you, Costa.
Thank you.
Do we have any questions? Please, can you go to the microphone?
Thank you for the talk. Very the names are amazing.
Robots are cool.
So my question is regarding the uncertainty estimation of the network. Current uncertainty estimation methods are shown to be overcomplicated wrong. Like even this often hard to talk about examples whatever. Did you find any situation where your epistemic uncertainty is low in the wrong way?
Yeah. So I think yes, but I think the most important problem. So first of all, epistemic uncertainty not being able to capture truly. I mean, with different samples, the true uncertainty we have in the neural network. I think that's straightforward. But the most important problem we have identified is when the depth image is such that the data that are captured in the depth image, they essentially barely reflect or very partially reflect what you truly have in front of you. So we had a particular case where we're trying to navigate in a forest at reasonably at high density, at reasonably high speed. And then we have very thin obstacles that we have to avoid, some branches that are 1 centimeter thick, right? And first of all, with traditional RGB sensor, you are capturing 2 pixels, if even, on this branch. So the fact that we're deploying deep ensemble essentially means nothing in practice if we have this situation, right? So obviously deep ensemble does not account for this because you have so little information that extrapolating out of it essentially does not work. To that end, we have developed a variation which is also open source, which we call semantically enhanced VA-based Oracle. And what it does, it takes the depth image and we attach a mask on everything that we consider, so it contains some manual work essentially, everything that we consider hard to perceive. And then the latent space compressed from the VA is now increased in weight to encode these hard to perceive obstacles. So thin branch, for example. We take this latent space, which is now essentially biased to capture particularly those hard to perceive obstacles and not do a good reconstruction of the remaining obstacles, which we don't, if they're big, we don't need to know exactly how they look, only we need to know roughly the geometry to avoid it. And then this has shown better results in this, what I would call sensorially degraded high noise environments otherwise. But anyway, to your question, of course, the deep ensemble will not handle every aspect of uncertainty in the neural net, especially if it is not present at all in the training data, which is not in the condition that I said. And then we do have some, I would say, more focused work on the particular problems we have on certain sensors, such as the stereo vision, to deal with limitations they have with stereo shadowing, capturing thin obstacles, and so on. Thank you.
Thank you. And just another third question regarding the IROS simulator.
Yeah.
Is it something officially supported by NVIDIA or is it just your own work?
We are using the official support ISAC, but it's our own work, right? So no official support from NVIDIA.
Thank you very much.
Thank you.
There's a question there.
Thank you for your talk. I'm kind of curious about how you handle the balance work part and the extended part and cost function, because
Yeah, I have give me a second to unload the hidden slide. It's I was expecting this question, so it's here. All right. So as you can see, I'm gonna go here so I can see also the screen. As you can see, essentially, we are waiting. First, for the uncertainty transfer, this is not quite straightforward, right? Every of them is one essentially a possibility of where the value of the partial state is. So we're creating essentially a weighted average based on parsing all the mean, all the sigma points through the neural network. And then for the different sample, essentially it's also the same. We are going through several layers of the different sample, and we're getting a weighted cost out of the different sample with respect to the likelihood that one of the motion primitives that we give. So as you can see, the method uses the decimals, the partial state, and a list of motion primitives. And each of them gets a score, and the score is weighted both in the sense of the uncertainty transfer that reflects the covariance uncertainty over the state, and from the different sample. We take the scores together and we find what we rank them all based on being the most safe. We take the 10% of the most safe paths, and from this subset of the most safe paths that we consider to be sufficiently safe, we take the one that gets us to the destination. All right.
okay, yeah, thank you.
Thank you. Yeah.
Thank you, Professor. And so I watched all the videos on the YouTube channel, and I noticed a new word, LiDAR regression stack. I'm quite interested in the radar part.
Yeah.
First question is, you are using the 3D radar or the 4D radar?
We're using, so I mean, a lot of sensors now are 4D radar. We are using a traditional PI that's a 3D radar sensor.
So XY and velocity.
Yeah.
And for the radars,
The methodology probably is like this, but it's correct. The methodology considered is like this, but it's correct for the policy. And then your next question?
yeah, the question is the more details about the radars. It's a point cloud matching based or feature extraction based.
So we're not matching point clouds. We are just using to get velocity update from radar storm. So
the equal velocity.
yes, and then we are essentially this is the formulation that you see roughly here, right? So we're getting velocity estimates from radar storm based on the Doppler equation you see there, and then we're just propagating, of course, over the body dynamics to create an odometry update. But primarily, our solution relies on for accuracy in the XYZ sense, relies on the fact that LiDAR for all degrees of freedom other than the one degenerate is accurate. For the degenerate one, when LiDAR has essentially in an extreme scenario, perfect similarity, no information, essentially for this freedom is radar that prevails completely over its combined optimization. Okay, so it relies on the fusion of the two sensors together most of the time. And also in my experience, even if we are in a subsimilar environment, it's not really subsimilar 100% all the time. So LiDAR still provides some good information here and there. But to your question, we exploit velocity estimates from radar, and we get traditional XYZ-based optimization to the positioning of the features of LiDAR that we register between point clouds and point clouds in the map in the traditional sense for LiDAR localization map.
Okay. And there are paper for this work.
That will be.
Will be released.
It will be released. Yes. For now, it will be released, but it will be released.
Okay, thank you very much.
Thank you. Any other questions?
Okay, let's thank our speakers.
Thanks a lot.
So yes, hi, I'm Effie, and I am here from Bristol, University of Bristol, and I'm going to talk about physically interactive robots. Sorry. I'm a Star Wars fan. I hope there are a few fans around here. So I grew up with Star Wars. I found all the droids in the movies fascinating and exciting. You can see a lot of them on this slide. And I think getting inspiration from science fiction is really important, and it can spark our imagination and feed into the research and what we can make possible. We actually had a showcase in Bristol in the summer where we invited a science fiction author in a robotics seminar to talk about that and how it can work vice versa. So writers also take inspiration from research they see on the news and try to imagine what can be possible with that. So my favorite growing up was R2D2, but unfortunately that's not where I ended up working on. I am working on Luke's robot hand. So I find robot hands fascinating, and I think they're really important. And I will talk about why that is a bit later. So physically interactive robots. What I mean with that is the interactions, the force and energy exchange that happens between robots and humans, either through the environment or directly with the humans. So that's mostly where all my work comes from, through looking into these kind of interactions. And of course, there is the object grasping and manipulation problem that is still open, especially for non-structured environments or environments for which the robots have not specifically been designed and trained for. So that is where I started working on through my PhD initially. So stable grasping and in-hand manipulation. My background is in control engineering, so I always want to see first how the system can be stable and how you can design a controller to do that. So I started with a simple enough experiment and assumption that we're working in a 2D plane. So doing an in-hand manipulation in 2D using just proprioceptive information, so only information that comes from the joints of the fingers themselves, the joint angles, you can do that in the 2D plane. So this is proved to be stable and robust to perturbations. Obviously, this is a simplification of the problem because the design and the theoretical analysis that has been done is in 2D. So obviously you cannot assume that this will work, but as you can see here, it generalizes quite well. Even though the motion is in a plane, the robot itself, the objects themselves are 3D, they're in a 3D space. So it still generalizes quite well. The other assumption here is that the objects are relatively lightweight. So all of them are very light. I'm not incorporating any weight estimation inside the controller at this point. So obviously, to extend that and create a controller that actually generalizes on every robot hand that we can have, because that is what we are looking for. It's dexterity that we're looking for. And dexterity is intertwined with our sense of touch. If you think about it, we can feel things. Every time we grasp an object, we hold the pencil, we can feel the edges of that pencil. So it's intertwined with what the hands are capable of. So obviously, robot hands would need to have that capability. And we, in the robotics lab in Bristol, we have this tactile sensor called the TacTip. I did not invent this, but I have been working on it and I will be talking about it. So this is a very simple introduction to the sensor. So this sensor is completely 3D printed apart from the camera that is inside. So it's an optical tactile sensor. And the black skin that you can see, it's soft. So it's a soft material. And inside that material, there is a pin-like structure. So the camera gets the images of that pin structure, and as it deforms the image, the pin array changes, formation, and you can use that to estimate different things. We can estimate 3D pose, so contact location and orientation, as well as force. Obviously, you need to, the way that we get these estimations is through training. So we use deep learning methods for that because their vision is so advanced, computer vision. So these are optical tactile sensors, and we can leverage those methods to learn those kind of things. So if you, during the collection, if you use a force torque sensor, you can get force data and learn that from the training. We are also gradually miniaturizing these sensors so that they can fit on smaller robot hands. So you can see at the bottom different robot hands that we have integrated the sensors with. And the one on the left hand side is the PISA IIT soft hand, if you've seen it. So that is a hand that is under-actuated. It only has one actuator, so it works like a gripper, but it has some mechanical functionalities that allows it to adapt around objects, which makes it really functional. So we have implemented and integrated tactile sensors on that, and I will talk about that more a bit later. And the latest miniaturization that we have is the one at the top next to the coin, which is still not published, but it's almost there. So going back to the stable grasping controller, I promise this is the only math equation in the presentation. So this is what the controller looks like. So it's relatively simple enough to write. It's a joint torque controller, and this one only uses proprioceptive measurements, again, from the fingers themselves, and tactile information. So in this case, it uses the contact orientation. So there is no object knowledge that goes into this controller. We know nothing about the object. Only uses joint angles or the Jacobian of the fingers, etc., and that contact orientation that we get from the tactile sensors. And it is proven that the closed loop system is stable. Obviously, the limitations are that this needs to have sufficient friction so that the fingers can roll on the surface of the objects, because it depends on that kind of capability from the fingers on the object. Because if you think about it, this is kind of how we do it as well when we are trying to grasp and manipulate an object within the hand. So like in hand fingertip rotation, we kind of roll our fingers around the surface. And then the next step would be to maybe do finger gating. So detach one of the fingers, keep rotating and reattach and keep doing that. But there is some rolling capability that needs to be there. And that leads to the next limitation, that the equilibrium, so the system needs to reach that stability within that rolling distance. So if that equilibrium is not reachable, so if the fingers need to roll a bit further, but through the mechanical structure they're not able to, then that will not happen. And the last one, which is in the good things and the bad things, is that it's a joint torque control. It's good because it can enable a lot of things, but bad because most of the commercial robot hands do not give you that access. So you need to control them through position, which limits what you can do with them sometimes. So this is kind of the idea of how the controller works. And these parameters at the bottom are parameters to do in-hand manipulation. So they're sort of rolling angles on top of the object, rolling distances. So after that, this was the extension to the 3D space, which is where, during proving that the system needs to be stable, we found that we needed tactile sensing because that was not the case in the 2D case. So in the 3D, you need tactile sensing to do that. And you can see here, the robot hand has these tactile sensors on it. This is the shadow modular grasper, which is kind of like a gripper. It has 3 fingers, but I'm only using 2 in this case. And the estimations of the contact orientation that I get through deep convolutional neural networks. So that's, they are trained beforehand on just a flat surface. So all the training and data collection is done only on flat surfaces, but still it generalizes well on curved and soft objects, as you can see here. This is a squishy kind of stress toy. And it's also robust to perturbations. So as you can see here, again, this is a limited kind of use case. There are only 2 fingers, and that can cause other issues to stability. If there is an external perturbation that is normal to that opposing fingers, then, and if the force is strong enough, then it will go out of the finger. So you need a third one at a minimum to consider that you can have any kind of stable grasp. So we extended this controller to 3 fingers, and these are preliminary results, so they're gonna be submitted soon. But we can see in simulation for now that the system is stable for different kinds of objects, also rigid and soft. So the duck toy is a soft toy, and this is in pi bullet simulation, which again is not the best simulation of a real environment. So experiments are coming up next. So when I talked about the controller, there were 2 parameters that allow in-hand manipulation, but as I said, they're not explicitly saying that you need the object to rotate a specific angle around a specific axis. There are more rough kind of parameters saying, I want the fingers to roll in that kind of direction or the other. So it would be very useful to know. What happened? One test? Okay, it's fine. It will be very useful to know how to map that to an accurate kind of orientation within the hand, to say that, for example, I want the object to turn around 90 degrees. What would those parameters be? So we did some initial experimentation of learning that kind of relationship between the estimations that you get from the tactile sensors and the orientation of the object within the hand. This was a very primitive way of getting some preliminary results, but they're very promising. So the next step would be to do it in a more automated way and integrate it in the grasping controller. So the next step would be to see how you can use this controller in a more advanced task, like human-robot interaction task. And I checked how you can do that in a human-to-robot object handover. So these videos, are they playing? Yes, they're playing. So these are, as you can see, in simulation, but they show that if you have 2 sets of fingers under the control of that controller, then you can use it to sense when that object has been released from one hand and transferred to the other. There is an extra term in the controller in this case, which is a kind of object weight estimator, but not exactly, because again, it doesn't use any information on the object itself, but it estimates from the joint angles and the fingers positions. So again, it only works if gravity is in this kind of vertical direction, and we have tested it in different kind of angles if the gravity is in a different kind of direction. But again, this would not work if the gravity was normal to the direction of the fingers as they are right now. And the next step was to test it in on a real robot. So we implemented the whole process of actually moving towards the target to do the actual handover. And for that motion, we used learning from demonstration techniques. So we encoded that motion into a velocity profile by using dynamical systems with the Gaussian mixture models. So that encoded the human demonstrators had the QR code on the wrist, so we tracked their end effector position and orientation. So that's what was encoded into a velocity profile. And we also found that it was easy to mirror. So we saw that if you try to approach an object or a target in front of you from one side, you will do a similar kind of motion on the left side. So we kind of needed to only collect data for one side, so halving the amount of data we needed to collect. So as you can see, the robot actually follows the target, even if the initial target location changes. And then the actual object handover uses that previous estimator. And for the weight estimation here, we use the joint torque sensors that the robot has to do it more accurately. So this again is like an industrial kind of arm. It's quite expensive, or it's using a finger, a gripper that is, this one is a barred hand, which is under-actuated, so you cannot fully use the controller. So it's a version of the controller that works with under-actuated hands. So we wanted to see if we try to do a similar task with an even more under-actuated hand. So this one is the PISA IIT soft hand that I mentioned previously, where we have integrated those small tactile sensors and did a simpler object handover. So the whole point of this work was first to miniaturize the tactile sensor, as you can see there at the bottom, so that it can be integrated with that specific robot hand, because each hand is different. So you will need to adapt the structure of the sensor. You will not be able to plug and play it with every robot hand. And the way this works, because this hand has a single actuator, and we have integrated 5 tactile sensors, one on each finger. So this kind of methodology is using feedback, tactile feedback from all sensors to do this task. So it was a way for us to see what more can you do with this so under-actuated hand if you had tactile sensing. And as you can see, it works quite well. It's using a very simple metric called structural similarity index. So the images that you get from the tactile sensor, you can use that metric to see the difference, how much the next image is different from the initial one. So it can detect very easily initial contact, but it saturates really quickly. So it can be used for gentle grasp, so grasp where you don't want to apply a big force. And that makes it also reactive. So if you apply a lot of force, it opens up back up. So that's why it can do the handshake very easily, because it doesn't grasp it very hard. And then when the human tries to release, it reacts and just lets the hand go. And it can also work with objects to hand over. Again, they need to be not very heavy objects, because the hand will open as a reaction if they're too heavy, because of the method that is used here. But we are working on a different kind of methodology, where we're actually using force estimations from the tactile sensors to do a bit more advanced methodologies at the moment. So I've talked about a lot of things about grasping controllers and how we can do things, but I haven't talked about the mechanical parts of the robot hands themselves. So what hands are available? Here you can see on one hand again, the PISA-IIT soft hand, where it is very underactuated, only one motor, and costs like $10,000. And on the other hand, you can see the shadow hand, which has 25 motors fully actuated, but also cost $200,000. So it's not very accessible to many of the research groups to do research on. And again, that demo here, and there was another one that was really cool, solving a Rubik's Cube. It only works for that specific task. And it took so much training and so much resources to do that. So the goal for me is to try and do these things as general as possible so that everyone can just get a hand, implement something, and be able to grasp and manipulate objects, which seems like a very simple thing to do, but as you can see, it's not so easy. So what we're trying to do is also build robot hands and open source the designs. So because we have this ongoing collaboration with PISA, as you have seen, I have mentioned this hand so many times, one of our PhD students worked on creating a 3D printed version of it. So obviously some mechanisms needed to be changed because the material is different, friction is different. It's tendon driven, this hand. So we had to work to see how we can have a fully 3D printed hand and how the tendon layout needs to be inside the hand in order to have the same kind of capabilities that the PISA-IIT soft hand has. And that is the soft adaptive synergies, which makes it adaptable around various objects. And we showed that it can work quite well in a wide range of objects. Again, very, very small objects or very, very heavy objects will not work as well. But we are working on a newer version with more advanced mechanism and also integrating tactile sensing as well. So another part of physical human-robot interaction is being able to do teleoperation. It's also a very big research thing. And it is also something I'm interested in because of the physical interaction and the haptics of it. So this is a project where we worked on robot-assisted minimally invasive surgeries as an application. And this is where we implemented a teleoperated system where you could feel the interactions on the robot end effector back on the haptic device that the user was using. And the work on the left-hand side was one of the partners where they implemented active constraints. So that means that it's a kind of artificial potential field that exerts these reactive forces. And we integrated that in the teleoperation so that essentially when surgeons wanted to operate, in this example, on the kidney, which is the green area, and they wanted to avoid the vessels, so the blood vessels, which are the red, then those areas would create those repulsive forces and wouldn't allow the surgeon to go into that area. Obviously, for safety concerns, there was a safety mechanism. So if they really needed, they could go in there. So you always need to have a good dialogue with people who are going to use this. Again, this is a very advanced setup with a cook arm and a haptic device that are usually costly. So again, we are trying to see how you can do something similar with low cost, and specifically in a way that is more related to robot hands. So a student of mine worked on creating an exoskeleton for the hand that is again 3D printed so that you can teleoperate a robot hand into manipulating objects. So the robot hand was the tactile Model O, so it's the open source Yale hand, but we have integrated tactile sensors on it. There is another paper on that. And what we did was create this exoskeleton very simple sensor, servo motors. The total cost is under $100. And it has rotary encoders to also track the joints and the finger motions. And it has a very basic mode of force feedback. One is completely binary, so just blocking the movement as soon as there is a contact, or also gradual force feedback so that you can sense the variable stiffness of an object. So this strawberry there is again a soft kind of toy, and we saw that you could feel the difference in stiffness between different objects. But again, it needs to be it's simple enough that it can break very easily. So it needs more research into how to make this more robust and maybe more powerful as well, because the servos are quite not very powerful, so you cannot get much feedback and much resistance. So that is from me, a little bit about me. As I said, background in control engineering, and then I'm now working in the University of Bristol. I would like to thank my team. So on the left, I singled out the people who actually did the work on my slides here. But on the right is us as a group, the Dexter's Robotics group, which is led by Professor Nathan Lepora. He has various talks around here at IROS as well. And he can tell you a lot more about the TAC tip if you want. He's the one that started it and worked on it. And also, I would also want to say that we have a project starting and we're hiring. It starts in November. It's going to be on bimanual object manipulation. And Georgia, who's actually a speaker here, is also part of the consortium. So we're very excited to start collaborating. And thank you.
Thank you, Epi. It's a very nice presentation. Do we have any questions? Yes, please. You would like to around the microphone, yeah.
Very nice talk. My question, first one is I'm wondering at the shape of the tactile fingertips, is there any influence in the design of the dome or spiral shape or other kind of shape?
Yes, very good question. So we started with a dome. So the original tactile was a hemispherical dome, but we have tested different kinds of shapes. So there is also a completely flat fingertip, and there is also one. What I haven't said is that inside the tactile sensor, it's not completely empty. There is a gel that makes it elastic and soft. So we have a version that is completely empty, and it can actually detect even vibrations on air. So that was a collaboration with Ultralib. But yes, we have different sizes, different shapes. So that one of the grasping experiments and the shadow modular grasper was like a triangular shaped sensor. So there are, yes, we can do different shapes of it.
And also like identify different thickness of object, very soft gel.
Yes, so I think when they first working on the tactile, when I was not part of that team, they had experimented with different stiffness of different gels, because you create the gel by mixing two substances. So if you don't have it exactly half and half, it might change how soft the gel is. So you can definitely play around with that. But the gel's consistency that we are using at the moment is proved to actually detect this kind of stiffness in the objects. So this can be done through the force estimations that we're doing. So we're learning the force, the contact force measurements, and estimated that. And that can be used to kind of, detect how stiff an object can be.
I have two questions. First one is when you showed the object handover class, how do you abstract out the action space for the robot for such a task? Yeah, second question is about this learning from demonstrations. How many expert demonstrations do you need to?
Yes. Okay. So the first one, can you explain? No, sorry. Repeat what you meant.
Yeah, the action space of the robot. Like, what was the action space?
Ah, yes. Okay. Yes. So that was purely on the end effector side. So it's not on the joint space and effector space. So it can be implemented on a different platform very easily. And the other question was,
How many expert demonstrations do you need to understand? Is it the task that can be done in minutes?
yes. So it was the demonstrations were done within I don't know, 2 hours or something. So we only collected, I think, I mean, the information is on the paper. I can't remember exactly how many demonstrations, but it was maybe 2 or 3 hours when we had people participate and do the demonstrations. No worries.
Thank you for the talk. I was wondering, you mentioned when moving from 2D to 3D for force estimation. You were doing a task related to CNN. And so I was wondering if that's because it's hard to determine the sticking model or definition of the sensor, or what that was.
Okay, so that was 2 questions. So from when I went from 2D to 3D, I realized that I needed extra information to prove that the system is stable. And that was when I figured out that I need tactile information. What I needed was just the orientation of that contact. So I wanted a sensor that can give me that. So the reason we are using deep convolutional neural networks on the sensor to get that estimation is because it's optical based. So you asked, sorry, about the deformation of the sensor, right? Yeah. So yes, the deformation basically makes the pins inside the skin change. I needed to have an image of how the sensor looks like from the inside, but it's like, imagine like a circle of a lot of pins, white pins. So if the sensor deforms, that pin array changes, so the pins move around, and the image that you get is different from the undeformed one. So it can learn that this kind of deformation means that contact location to contact pose. Does that make sense?
Yeah. I have some questions. One was, you have a link on the fingertips, and do you ever find it useful for dexterous tasks? Is it like also on finger?
Yes. So for now, we've only used it on the fingertips. There is some work using soft grippers. So the fingers are soft structures, and we have a tactile sensor on the palm to detect probably contact and some other things so that the gripper closes. So yes, we are exploring how we could use this on a kind of skin-like structure. The problem with that is that you need the camera to be able to detect the whole surface of the skin, and that's where the challenges come in. But yes, it's mostly on fingertips for now, and we're experimenting with implementing maybe the palm and seeing how we can expand to a skin-like sensor. No?
Last question.
Okay, so thank you for the very nice talk. So I have a question about the exercise that you presented. Nice for the version. I was wondering how natural is the feedback that you can get? Because when you touch something, you get pushed on this part of the finger, while your system kind of pushes on the other side.
Yes, so exactly. That was part of the design, so that you didn't feel the pressure on so we put the servos on the back of the palm so that it would move the structure back, kind of stop it from moving forwards. So you cannot feel like the texture or anything because there's no tactile sensor on the fingertips. It's only a wearable to stop you from moving towards that direction. So to stop you from continuously to closing the grasp. So, but there is a structure where you can feel that you can not move your fingers any longer.
But it's a sort of kinematic.
Yes.
Kind of.
Yes.
Isn't this tool kind of disturbing the user experience, something like that? kind of, being something unnatural yesterday?
It's funny because humans are very adaptable, so they can learn very easily that this sensation means that. But it's similar to this. If you have used any other exoskeleton, like commercial one, it's a very similar sensation. So it kind of stops you from moving forward. And sometimes it's just because it learns that point. So you can move your finger, like your joint fingers around, but that point cannot move forward further. So it's a kind of weird sensation. You cannot have feedback on the whole of your fingers. It's only on the fingertips. Yeah.
Thank you very much.
Thank you. I feel let's thank Becky once again. Okay, welcome back, everyone. So we will continue with our keynote presentations. We have Roberto Martin. He's an assistant professor at the University of Texas, Austin. And his talk is about perceiving to interact and interacting to perceive. Thank you very much. Stage is yours.
Thank you. I actually dropped the first part because I realized I'm mostly talking about interacting to perceive. So let's focus on that. And that was actually how Nikolai approached me for this workshop. He told me, this is going to be a workshop very related to a workshop we organized with Carol back in the day on how to use interactions to perceive and how learning can help on that process. And that is what I'm going to be talking about today, how to exploit interactions in perception and how learning can actually help us with that. And I want to talk louder. Okay, I'm going to scream, or maybe I can get closer. All right. Okay, I will try to be quiet in front of the microphone. All right. Good. Yes, so I was saying, I'm talking about interaction to perceive and how to integrate it with learning. And yeah, why am I talking about this after a few years that we did that workshop? Because we have a lot of advances, but I would argue that we're still not there. We want to be able to exploit more interactions with our robots so that they can perceive the world in a better way, at least how humans perceive the world. And I'm going to show you a video that demonstrates how much humans use interactions to perceive the world. So this is a video from a video blogger called Rachel Papworth, and she gives us tips on how to have a tidy and efficient life. And in this video, she talks about how to calmly and efficiently find the thing when you've totally gone and lost the thing. So let's listen to Rachel, and then we will see some parts of that video. I hope you can hear it. No, you cannot, but that will be fine. I put subtitles because audio never works in this thing. So you can see what she's saying. Basically, trying to find something drives her bonkers because the things are never where they should be. And this is how we feel many times in our lives. And this is, if robots would have feelings, they would feel the same way trying to find objects in our houses. So let's see some more parts of this video because the video is longer and Rachel tells us more about how to search for objects. So here we see her searching for objects in a house, finding objects in a cabinet, then getting bonkers, like she said, and trying to find the object under the pillows in the sofa. And at the end, what she tells us and her advice is to keep calm and try to find the objects in the more logical place where they can be. So that is what she does here. And what I find interesting about this video is, of course, perception is guiding her interactions. She wants to open a drawer. She looks at the drawer. She goes there and acts on it. But a lot of interactions help perception and guide perception. She searches for objects, she pushes other objects away, she opens mechanisms. And even when she opens a mechanism, the interaction reveals how this mechanism should be interacted with. So there is a loop there to perceive the information. So this is not a very new idea in the science of intelligence. There have been a lot of studies on how biological agents and humans use a lot of interactions to help perceive the world. Already in the 60s, a psychologist called James J. Gibson enunciated his theories about how biological agents seek for information instead of just receive it passively. That is what is called interactive perception. Use interactions to reveal information and to interpret this information. So how the interactions are used is a twofold process. The first one is to create information that may not be available first, like for example, when we unocclude an object and then we create visual signals that were occluded before. But also these interactions allow to interpret the sensor signal in a richer way, like when we interact with an articulated object and we feel what the constraints are and we see the motion. So this is all through the interpretation on how we interacted with it. So James J. Gibson explored that in a very simple experiment where he asked participants to identify a pebble among a group of pebbles, and he distinguished the groups of participants in three. The first group would only see the pebbles and try to match the given one to those, and this group achieved only 50% success on the task. A second group could see the pebbles rotating, videos of the pebbles rotating, and this group achieved 72% success. But if you give the opportunity to participants to decide on how to rotate the pebbles actively, you achieve 99% success, almost perfect. So the key idea here is that by interacting, people are able to perceive much better. So the scientific question here is, how do we enable robots to do something similar, to create and interpret informative interactions? So that's what I've been doing in my research in the last few years. And mainly I apply this idea to two domains. In the first domain, I enable robots to create interactions to unocclude objects, and something that we call mechanical search or interactive object search. And that's mainly what I'm going to be talking about today. And in a second line of research, I enable robots to interact to reveal parameters of objects, for example, kinematics or dynamics, friction, parameters that are very useful to manipulate those objects. And I will touch on that at the end in relation to a new hand that we have developed that enables this type of interactions in a safe manner. All right, let's talk about the first question, how to generate interactions to unocclude objects, to perceive new objects. In computer vision, object detection is a passive process. Given an image, you have to detect where is the object of interest. But as we have seen in the videos, if you are an embodied agent, you can interact and create the signals that allows you to detect the object that you're looking for. We call this problem mechanical search or interactive object search, and we define it as follows. Find and retrieve an object X in a pile in a physical environment with several other objects that may be unknown or known, while optimizing some quantity of interest, either time, energy, amount of interactions, etc. We look at the first version of this problem in the problem of searching for objects within a pile of objects. This is a problem that appears a lot in logistics centers, but also in homes, like we saw Rachel looking in the drawer full of objects. So the idea here is we tell the robot what object to look for by giving it an image of that target object, but this object is in a pile of unknown other objects. And what we created is a solution where the robot uses interactions, grasping, pushing, pulling, in order to unocclude the target object and retrieve it. I'm not going to go into the details of this system, but I wanted to show you what the system does at the end. Here we see the agent looking for the object that is initially visible and that we are going to be occluding with a pile of objects. And it just uses a combination of grasping and pushing based on current views to unocclude the target object and retrieve it here at the end. So our system achieved 92% success on finding objects in piles of objects. This was an initial collaboration on mechanical search that we did with our colleagues from Berkeley, from Ken Goldberg's lab. But in a different extension of this work, we went into exploring finding objects in large scenes, like homes, where the objects are not just unoccluded by a pile of objects, but actually organized in a semantically meaningful manner, like what objects are in different rooms or in containers. Here, the actions of the robot are not just pushing and pulling, but it also needs to decide where to go. So it needs to combine locomotion and manipulation in mobile manipulation tasks. So in this new problem instance, basically the agent needs to first move to a room to search for the object, maybe furniture containers in that room, like for example, going to the kitchen to try to find a white mug, then deciding in the kitchen what container to open and interact with to see if it finds the object. And once that it interacts with that container, decide if it searches further, if it's not visible, by, for example, removing some of the objects that are in that container, like in our previous version of mechanical search, or go to another container. And it will be doing that until it finds the target object that is commanded to find, which, by the way, the command here is a language description. So at the time we were doing this, looking at the literature, there were two main families of solutions. The first one, which was also what we were doing before, looks at this type of object as an object retrieval in Clutter, where the information that is important is the geometry, how could be occluded the object that I'm looking for. And this type of problem is usually rendered as a table top problem. A second family of solutions were looking at this problem as a visual navigation problem. I have an agent, it can move around, for example, in a house. The objects are organized semantically, but that agent cannot interact, can only move around and look. So we wanted to combine these two families of solutions into a solution that can navigate, but also interact to try to unocclude and combine information both from semantics, where is the most likely location of an object to be, but also geometry. Where are the objects that are occluding? Should I look farther and try to find if there is something behind? So to solve our mechanical search problem, a first question we faced was, what should be a good representation to solve that problem? How do we encode this structure of having rooms with containers, with objects? We then decided to use a hierarchical scene graph as a representation for our problem. Scene graph is a representation where the nodes represent entities like rooms or objects with information about the geometry, their location, their size, their bounding box, but also their semantics, what class of object or room it is, RGB images of them, etc. We grow this graph dynamically as the agent is exploring the environment. Now that we have a good representation for this problem, so the second question is, how do we make use of it and decide on what actions to take in order to find the object that we are looking for? What we propose is a method that we call HMS, Hierarchical Mechanical Search, that combines geometric and semantic information at the different levels on the hierarchical scene graph to make decisions. It decides on what room to go, what container to open, or what object to remove based on the combined information of semantic and geometry at the different levels, propagated through the levels with a message passing mechanism. So this combined information will tell the robot to go to the kitchen because there is a pantry there that is the most likely to contain the object, like the white mug in this example. So how does this work? For a given parent node in a graph, we combine the geometric and semantic information in a feature vector. And we do the same thing for the children nodes in the hierarchical graph. We then combine the information between parent nodes and children and vice versa by passing the information up and down and creating new features that contain the combined information. When we have done that, we also represent the target object as a feature based on the language description. And what we are going to do at the end is combine for each node the feature that represents the node, the feature that represents the target, and query a classifier. What is the likelihood of finding the object that I'm looking for in this container or behind this object or in this room? We train this classifier in a supervised manner with annotated ground truth from houses full of objects. Nowadays, an alternative would be to query a large language model that contains this common sense knowledge. We evaluated HMS in 500 houses in simulation and compared it to variants using only geometric, semantics, or flat information without message passing. And our solution achieves the lowest number of actions to find the objects, 13.8 of mean number of actions, thanks to the combination of semantics, geometry, and the information from other levels. On the right, you see one of the executions of our solution. on a top-down view of the robot first, then the robot decides what room to go, which is the kitchen because it's looking for a yogurt. Then it goes into a container like the fridge because it's the most likely location, finds some other objects that are possibly occluding the target object, like the other milk product that is there, I think butter, removes it and finds the target object that is the yogurt. So you can see that it's doing a little bit of what Rachel was advising us to do, trying to be calm and locate the most likely location. All right. So in more recent extensions to this work, we tackled some of the real world problems that this solution had. The first one is what happens if a robot enters a new house and this house had other agents, like for example, humans. That means it needs to build incrementally the scene graph, but at the same time, the scene graph could be dynamically changing because the other agents could be changing the location of the objects. So we map this problem into a problem in communication theory that is called link prediction. And what we do in essence is to hallucinate what is the most likely location based on the previous observations of the robot, but without trusting 100% the current hierarchical scene graph. We presented this at ICML this year. And then a second extension was more on the side of how to command the robot. Many times we want a specific instance of an object, like bring me the red mug that is on top of the coffee table in the kitchen. This type of definition, we call it hierarchical relational because it's based on this hierarchy of where the object is, room, container, and relational because it relates to other objects in the scene. We presented this work at ICRA this year. So I'm not going to go into details of these two works, but I'll leave you here the references. So if you are interested, I'm happy to discuss further after the workshop or later on email or in a chat. And I want to thank my collaborators for this work. All right. So all these solutions work at the task level, where to go, what container to open, but actually how is that skill implemented on a real robot? All these skills in the most general form are mobile manipulation skills. So in a parallel line of research, we explore how can we learn to control a robot for mobile manipulation skills using reinforcement learning. But what is difficult to apply reinforcement learning to mobile manipulation? It's not a direct thing. Well, in mobile manipulation, there is a couple of kind of like caveats when you try to apply reinforcement learning directly. The first one is the dimensionality of the action space. You usually have to move the base, but also the arm and the gripper and possibly the head. This clicker is not really working. To try to keep the objects of interest in the field of view. And this is on the side of the action space, but also on the side of the objective of the task is usually multi-objective. So you may have an objective that is to reach with your hand at a position that is the most common objective, but at the same time, you don't want the robot to collide. And if you're based on vision, you may want to keep the object in your field of view. So all of this makes the problem quite complicated because you have a lot of action dimensions, a lot of reward terms, and if you pose it naively, you're going to try to optimize all the action dimensions based on all the reward terms, which leads to very large policy gradient variance. And that makes very unstable reinforcement learning training. So we were thinking, can we actually simplify this? And we find a good way to do it. We realized that not all action dimensions actually matter for all the sub-objectives in your mobile manipulation skills. Actually, if you think about it, many of them do not really matter for achieving the sub-objectives. So what we did was to try to use this causal dependency between action dimensions and reward terms to obtain reduced policy gradient variance and more stable training. So we encode this idea in a new solution that we call causal MoMA, that is a two-step procedure. In the first step, we infer the causal dependency between action dimensions and reward terms, first by interacting randomly with the environment. Then, under some assumptions, we prove that the action reward causal dependency can be reduced into a causal mutual information check. You can see here the equation, but the main idea is how much more do I know about a reward term if I know about an action dimension? If knowing about an action dimension doesn't change, how could I predict my reward term? That means it's independent. So that is the main idea. We use this idea to basically create a matrix that tells us what action dimensions are causally correlated with reward terms. And with this matrix, we can go back into our reinforcement learning algorithm and update in our policy gradient just the action dimensions that are correlated to the different reward terms. So this cleans the process and makes the process more stable. We tested that in simulation with some simplified mini grid with manipulation tasks, but also with Gibson, where different robots try to achieve mobile manipulation skills using joint space or Cartesian space. And we observed that by using this factorization, we achieve significantly larger performance. So the interesting thing is that we took these solutions created in simulation and we went to the real world in a sim-to-real transfer process. And we see the robot here being controlled with this policy training simulation, achieving, reaching locations that are moving, avoiding obstacles that appear in the way, and in a more efficient way compared to motion planning and optimal control solutions. So here you see a couple of other skills where the robot pours a liquid into a container and follows a person while avoiding obstacles and keeping the target in the field of view. This is coordinating all base, arm, and head motion. Right. This was a collaboration with my student Yaheng and with Peter. All right. And in the couple of minutes that are left, I want to mention very briefly the other line of research that I have on how to use interactions, or how robots can use interactions to reveal parameters, especially for articulated objects. Objects like doors, drawers, laptops, many tools, where knowing how they move actually requires to first interacting with them. So that's what I was doing in my PhD back in the day. And here you see some examples where the robot interacts with objects that can be transparent, or even when the lights go off, because it integrates vision, proprioception, tactile sensing. And it infers what are the kinematics. You see here some green and red indicating prismatic or revolute, and how many degrees, how much they are being interacted. With this information and dynamics that are also extracted, the robot can plan interactive actions, like here where it's planning how to interact with this object to find the articulation. And we can combine all of this to try to open complex lockbox mechanisms where there is joints that are locking another joint, and it needs to find all these joints and their interdependency in order to open and solve this kind of like puzzle. So one thing that I want you to look at here are the hands that I were using in these experiments. So in most of them, I was using the soft hand that was developed in my lab back then in Berlin with Oliver Brock and with the creator over here. So that hand is great. It's soft. It's very safe. You can interact. You don't break things. You don't break the robot. But there is one problem, Rafael. I'm sorry. Sometimes it's not strong enough. For example, for the last experiments, we couldn't actuate it with the soft hand. So we need to go back to the hard hand. But hard hands in robotics, they are tricky, especially with articulated objects, or we want to interact to perceive and we don't know what is going to happen because it's risky. They are brittle, they can break things. So we were thinking, can we find a new compromise between these two things, between the compliance, the collision tolerance of soft hands, but also the precision and the strength of hard hands. So we developed in collaboration with mechanical engineers at UT a new type of hand that is called Variflex, that tries to bring together the benefits of soft and hard hands. So the main components of Variflex is a direct drive actuator that allows it to be compliant when it contacts the environment, and a combination of soft and rigid linkages that are also adaptive to the object to grasp. And all of these for less than $500. here to show you some of the things that Bariflex can do. It can grasp an object in the expected pose, but even if there is noise in position or on orientation, has a large aperture, so it kind of like grasps without problem. Also, if the object is small, like you see here, there is a knife that is kind of like very thin. You can grasp it without problem because it can do pinch grasp, and also it can be compliant and adapt to the shape of the objects. So what we were looking for Bariflex, I came to my mechanical engineer colleagues and I said, I want a hand that I can do everything in a home with. So versatility, it was a very important design decision. So here we see that we can use it for very heavy objects. We kind of like hook with it, and it's resistive for opening big doors, fridge, etc. But it's also very fast thanks to the direct drive, and it can grasp objects that are falling. It moves really, really quick if you want. Here another example of versatility. Here we're one of my students is manually controlling the hand to fulfill a complete long horizon task, which is preparing instant coffee. And every step here can be perfectly done with the hand. Now, my mechanical engineer colleagues came back and say, well, now computer scientists, you have to create the algorithm to use the hand. So that is what we are going to be doing next. But look here, pressing buttons, that was always super scary for me with our hands. I'm going to break the microwave. This hand is great. It's kind of like super compliant. It's the right balance. And it's very robust. So they were doing these very good experiments on testing how much force you can apply and repeating hundreds of times and really being mean with the hand. And it's still not breaking and capable of grasping objects in a good way. But for me, the important thing is I want to interact to perceive, and I want to be able to learn with it. And here I asked one of my students, Arpit, to do a real-world reinforcement learning task where it just learns to grasp an object by trial and error. That's what I want to do with a hand, and this is what this hand enables. Right. So this is a collaboration with Kushal, Arpit, my student, and Ashish. And with this, I come to an end. The key takeaways, I think interactions are really necessary to perceive the environment in the ways humans do. Robots have to reason about how to create these interactions that are the most informative ones. Like, for example, when searching for objects, you combining geometry and semantics. Learning to manipulate, do mobile manipulation is easier if we exploit the causal dependency between action dimensions and reward terms. And finally, the robot embodiment matters a lot. If we want to use interactions to perceive and to learn, we need an embodiment that is robust for that. All right. Thank you, everyone. And I'm happy to take some questions now.
Thank you, Roberto, for this presentation. We have any quick questions? We have time for 2 questions. Can you please join the mic?
Yes.
What heuristics do you use to decide you've gone the wrong way? How do you decide you've searched enough and you should try again?
Mm-hmm. That's a very good question. And it's also a question we had when we were working even in the trustable version. How much deeper do we need to go? This is something that we let the agent to learn for. And it basically tries to find the optimal way based on the previous experiences. So here we pose it based on experience. But we were thinking, because here the cost of an action is always 1, and that is what the agent tries to optimize, the least number of actions. But removing an object from the place where I'm looking at is less costly than going to the next room and open a new container. So we want to explore how to actually incorporate more semantically meaningful costs, because then the strategies are going to change. I may go deeper into where I am because the cost is lower. And at some point I will give up and go somewhere else where the cost is larger because I need to move there. So yeah, that will come later. But right now it's purely based on experiences from the agent. It will decide if it should go deeper or switch to another place.
Yeah, actually my question was quite related. How you deal with some perception failures, You said 90% accuracy, which I presume sometimes the object is there and you don't find it, but about detecting the object when it is not there. So some of these perceptions can fail.
Yeah. So in the first version, that is part of the 92. It may be visible, but we don't see it with the perceptual algorithm. It may be that it thinks it grasped the right object, but it was a failure. So that was all part of it. In the second version, in the more larger scene version of it, we added noise to the perception because it was mainly in simulation. We wanted to incorporate what happens if the object is visible, but the perceptual algorithm doesn't see it. And then the agent still copes with that. So our results are with noise in the perception, but we don't do anything special to cope with it. I think that, yeah, that's a very good question. Sometimes the agent is gonna just fail because perception, not because they're taking the wrong decision. Yes, that's right.
Cool. Let's thank Roberto once again.
Thank you.
So before we move on, I would like to say that one unique feature of our workshop is actually we decided to give the microphone to some early career researchers. So we invited people to submit abstracts of their PhD research. And today we have Peter from and he received the MoMA award, finally sponsored by the Technical Committee of Mobile Manipulation. So let's congratulate Peter.
So despite amazing progress in both robotics and AI research, today, the majority of our robots are still confined to environments like factories, where they basically solve a narrow set of tasks in a structured environment, far from humans. Now, the robots that really make me excited are more like this, where they solve a large set of, tasks in previously unseen environments, closely interacting with humans. So towards this kind of like human level robot intelligence, a central question is how we can combine structure and knowledge with the ability to learn from experiences. And to this end, I'm going to introduce in this talk the differentiable algorithm networks, DANs, which is a general architecture for designing scalable and compositional robot learning systems. So I want to start with discussing how we are kind of building robots today in a very high level. There are two main design principles, the model-based and model-free. Now, in the model-based world, we basically first build a model of the environment, and then we are going to use some inference algorithm to reason with this model. And so we derive robot actions based on this reasoning. And our system, of course, might have more than one module. So we might have a module for perception, state estimation, planning, and control. And the benefit of the strengths of this model-based approach is that it is composable and it is interpretable. Right? However, at the same time, there are issues about approximations we have to make. Right? So first, it is inherently impossible to model the real world perfectly. Right? And even small modeling errors are easily amplified through the reasoning processes. And second, even if we had a perfect model, we would oftentimes need infinite compute to solve for an optimal action. So therefore, we are always forced to make approximation both on the modeling and the algorithmic side. And these approximations make the system brittle. right? And they require a lot of engineering effort to then integrate into a working system. Partially in response to this, the other side and the model-free approach represents the entire system as a function, typically using a neural network, right? And it then trains this function end-to-end from sensor to action. This is great because through this end-to-end learning, the system becomes robust to what it is trained for. So say the task distribution we kind of wanted the robot to solve. However, typically the learned solutions are narrow because these models lack strong priors that would allow them to generalize to a large set of tasks with limited amount of training data. And second, the models lack interpretability, which of course are kind of important to derive any kind of safety guarantees, especially important for safety critical applications. So one kind of key insight of our work here is that while these two sides here, the two design approaches, seem to make conflicting design decisions, they are in fact can be resolved if we rephrase their key strengths. So on the left side, the model-based approach, in fact, talks about how a system should be structured. It says the system should be modular so that the knowledge captured in models can be recombined in combinatorial number of ways to solve large set of tasks. The right side talks actually about how the system should be trained. It says we should be trained end to end so that we can make the system robust for the things we care about, and we are directly optimizing, for the task we want. And so if we put them this way, then we have a hope to combine these two approaches and develop new architectures that are modular and end-to-end trainable at the same time. So differentiable algorithm networks attempt to achieve exactly this. And the key underlying idea for this is to encode algorithms into neural networks. So what does that mean? So all neural networks we can understand as just a form of computation graphs. Computation graphs have some learnable parameters, and we have some operations acting on these parameters, right? And so differentiable algorithm networks are also computation graphs. The main difference is that some subset of these fixed operations that are in neural network, these are non-linearities and such. Here, they implement an algorithm. And what I mean by algorithm is something like a planner, a controller, a SLAM, something like that. And then some subset of the learned parameters can be associated with a model. So say like a dynamics function of an MVP, right? And if we think of them this way, then this network can be trained the same way as a neural network. Basically, we can update learnable parameters by backpropagating gradients through the algorithmic computation. The only requirement and the key requirement we have is that all these operations in the algorithm needs to be differentiable. And so as long as that happens, we can all do this, new deep learning style learning. So the key question we need to address is how to deal with non-differentiable operations. And I will not have time to go into details here, but in the past several years, there have been various ideas proposed to deal with different types of non-differentiable functions. So for discontinuous functions, like a max function, we can do continuous relaxation. We can replace it with softmax. For sampling from distributions, it's also a non-differentiable operation. We can use the reparameterization tricks if our distribution is a Gaussian. For discrete distributions, we can do Gumbel softmax, a straight-through estimation. In some cases, we can use important sampling. For certain types of larger computation blocks that perform some sort of iterative fixed point computation, we can use the implicit function theorem to derive analytic gradients. And then finally, the last point there is that for any non-differentiable computation block, actually we can resort to score function estimation to estimate gradients, with the caveat, of course, that those gradient estimates are going to have a high variance. So using this set of ideas and others, recent years, there has been a number of differentiable equivalent of classic robot algorithms proposed in the literature. This includes some of our work and many of other people's work. So we have differentiable, state estimation, differentiable localization, mapping, SLAM methods, differentiable planners for MDPs, co-MDPs and graphs, differentiable controllers and optimizers. So again, this is just a small subset of the differentiable algorithms we already have. And these papers are actually only up to 2020. So please forgive me if I kind of forgot or didn't include your favorite example. The point I want to make here is that if we have these differentiable algorithm components, we can then compose them to build entire robot systems, right? Where a single computation graph is going to capture multiple modules. And we can train all learnable parameters we choose to have in the system end-to-end by backpropagating gradients all the way from the output loss through the algorithmic computation back to the parameter. Okay. To understand why we want to do this, what's the benefit? Let's look at a case study for visual navigation. So here the robot is in a new environment and needs to reach a goal given first-person observations and a top-down map. The details are not that important, but here we tried to construct both like a standard modular architecture and an end-to-end neural network type architecture. And the both of them achieve some success in generalizing to new environments, but they're not perfect. The interesting thing is that then we tried at them that takes the exact same modular decomposition, same model function, same algorithm as the modular system on the left, but then trains its models end-to-end, just like the system on the right, the same imitation learning data. And so this then achieves a 99.8% success. Let's look at why this happens. So I want to kind of separate the two sides. Now, on the right side, we can understand both systems as some form of neural network approach, right? Both of them just have some learnable parameters and they're optimized with imitation learning data. The difference is that in then we have some structure prior that we imposed in the system. This is some form of inductive bias, which happens to take the form of algorithmic computation and decomposition, right? Other than that, this is just the two kind of neural networks we can understand. And of course, this structure is useful, kind of same way as how convolution is useful for object detection, right? Just here, the structure is an algorithm. The left side is maybe less intuitive at the first side. So in this case, both systems have, during inference, they do the exact same computation. The difference is in how the models were trained. The left side, how we normally train models, is we ask them to be accurate, describe the word accurately, and then kind of trains the models to be useful for how they're going to be used in the planner or in the subsequent algorithm. So we are kind of like, in this then maybe we learn wrong models in that they are not necessarily accurate, but we learn models that are useful for how we're going to use them. Okay, and I want to kind of show you a concrete example how a wrong model can fix a kind of wrong approximate algorithm in this way. Okay, and that in the same domain, what we tried is to purposefully choose a too short planning horizon in our planner. 25 steps. The goal is sometimes way further than 25 steps. So there's no chance that this planner, can find any reasonable plan in those cases. Indeed, success rate is only 59%. Interesting thing is, we took the same planner, same planning horizon, made it differentiable, trained a model, in this case, the transition probabilities, with imitation learning data. And magically, this then now can solve almost all the cases. Why is that? Here I'm showing you the transition matrix. This is a discrete underlying word. So this is just the transition probabilities are just a matrix for the turn right action. And again, it doesn't matter, but what you see there is that for turning right, there's a probability of 1 for the robot to actually turn right. This is ground truth model. Nothing interesting. Now, in the then, we learned these probabilities. And what we find is that the learned probabilities assign a high value for turning and moving forward for the turn right action. Now, this is a wrong model, right? Because in this domain, turn right action will never result in forward motion, right? But you can imagine how this transition model reduces the effective planning horizon required to solve the task. The same as how we normally design macro actions, right? So through this end-to-end training, our model learned to invent its own macro actions that help it plan with this deficient planner, right? Which we purposely set this thing just for the experimentation. But even in the real task, we found a number of sometimes intuitive, sometimes not so intuitive ways of how this end-to-end training can fix approximations we have in the decomposed system. So in the interest of time, I just mentioned them very briefly. So if we, with our transition model, for example, didn't capture obstacles at all, this then learned to compensate that by inflating collision penalties. So the robot stays away from the obstacles in the first place because it can't model them. Our system couldn't plan for information gathering. So this then invented rewards, kind of shaped rewards, so that it incentivized information gathering action. And our perception system in this case often led to poor irreversible actions, which then compensated by essentially learning to communicate confidence between perception and decision making. So to summarize the point so far, we have this differentiable algorithm network, then architecture that can be understood from both perspectives. From a structural perspective, it can have the same modular architecture as our kind of classical robotics requires us to do, with the additional ability of training models in a task-oriented manner. We can also understand this then as just a neural network architecture. From a learning perspective, I have two neural networks, but one just encodes a structure prior in the form of algorithms. And the reason why I kind of also find this quite exciting is because we can think of this as a neural programming framework where we are able to capture both algorithmic reasoning as well as neural network type representations in a single conceptual framework, which then really opens up the entire spectrum of designs between fully model-based and fully model-free. So let's look at whether these things actually work. There are a number of applications of this framework. I picked 4 here from my own works, and I will mention them very briefly only. So in one work, we developed a differentiable particle filter with learned transition and observation models, and then applied it to a robot localization problem where the robot has to localize in a previously unseen environment, given first-person images and this a floor plan. And what you see here is that the robot successfully localizes. Okay. We also extended this work to differentiable SLAM, and this is in the habitat simulator. Here, the robot is simultaneously localizing and mapping the environment. In this domain, we found that the differentiable SLAM outperformed both the learning-based alternatives as well as ORP SLAM, which is a very popular SLAM technique. When we connected this to a downstream planner and submitted to the habitat challenge at the time, it came on top of the leaderboard. We also managed to do some sim-to-real experiments. We deployed the models learned in simulation to the real world on a spot robot. It's navigating our university campus with this arbitrary clutter that I've shown around there. And then finally, this is the topic that I'm currently working on at NVIDIA, autonomous driving, where we are trying to kind of apply similar ideas to develop next generation AV architectures. And if I have time for this, I want to kind of just say a few more words about this. So again, the high level in the autonomous vehicle space, there is again the same kind of conflict of high level approaches, how companies and research is addressing autonomous driving. One is model based, one is fully learned. And we are kind of trying to do something that fuses the two and develop these modular yet end-to-end differentiable autonomy stacks. And specifically, we looked at the prediction, planning, and control tasks. And we kind of started with a standard stack. It's fairly kind of standard architecture for driving. It has a prediction model that tries to predict the future motion of other agents on the road. It has a planner, and it has a controller. Now, in the standard version of this, we learn the prediction model, it's a neural network, and we handcraft the planner and the controller. Now, what we did in our differentiable stack, we call this diff stack, we made the planner and controller differentiable. They still fixed, but differentiable. And then what we could do then is to train the prediction model for a combination of a prediction objective and planning and control objectives. So, and then we kind of backpropagate these losses through the controller and planner. So what we're kind of doing here is that we are learning this kind of task-aware prediction model. We compare the two architectures in a new scenes data set, and we looked at prediction performance in terms of average displacement error and the planning cost. This is a percentage with respect to a theoretical best we can do. And what we saw is that while the two stacks perform similarly in terms of prediction, the differentiable stack performs much better in planning. Right? Because we were able to kind of train our prediction model for the planning task. And again, it's important to emphasize here that at inference time, the two stacks perform the exact same computation. The only difference is how we train the model, right? And that kind of also shows that I mean, people in this space typically compare prediction models only based on this kind of ADE type prediction metrics. But as we find that they don't really translate necessarily to how they're going to behave in planner, which is also consistent with what we see in practice. I will skip through the reasons why exactly this happened in the interest of time. But I just wanted to say that these are just, of course, first step set of results. We actually want to develop full end-to-end differentiable autonomy stacks, including perception, which will allow us to do all joint training across the stack, and beyond that, also to learn new interfaces between modules and propagate uncertainties better. So one kind of current direction that we are working on is, in fact, to learn an interface between perception and planning for autonomous driving systems in a self-supervised manner. But I will not have time to discuss it anymore. So I just want to kind of summarize my points so far, I mean, in this talk. So if you remember one thing from this talk, I hope that is going to be that we can build in algorithms, classic robot algorithms, into neural networks. And if we do that, then we really come to this kind of new design approach that can combine the modularity principle of the classic robotics with the end-to-end learning capabilities of like a modern machine learning type approaches. This framework has applications in many robotics domains, including autonomous driving. Okay, so with that, thank you very much for your attention. We are hiring. Contact me if you're interested.
Oh, thank you, Peter, for this presentation. We have time maybe for 2 questions. If someone wants to ask a question. Yes, please.
Thanks for presenting the very good topic. We have to understand how the normal model, when you combine the BNN, resource constraint, is it using more resource? For example, if you run an engagement GPUs compared to an embedded system which is really there on the vehicle, how do you think? And what are the negatives and positives?
So you are asking about the difference between a differentiable model and the original model.
That's right.
Yeah. So it can be, I mean, either. So there's no single answer. In some sense, for example, in the example that I showed for indoor navigation, our systems actually the exact same at inference time. So they require the exact same computation. Right, the model class is the same, right? I showed you those, like just the transition probabilities. So the computation doesn't necessarily change. What changes is how we train the models. So that's one thing. The other part of my answer is that sometimes by doing this end-to-end training, we can in fact reduce the computation of that classical system by learning something that compensates for that works with a less, for example, less planning iterations, right? Again, the same example I showed you, right? I chose a planning horizon that's too short, but then I can learn a model that compensates that short planning horizon. So if at inference time I'm only can afford to plan to a certain horizon, in this framework you have a chance to kind of come up with something that works with that short planning horizon. So maybe invent a macro action. Hope that answered the question.
Thank you. Let's thank Peter once again. So we are moving to the panel discussion, robot perception for navigation and manipulation. We have Coline Devin from Google DeepMind, Psomopoulou from University of Bristol, Peter Karkus from NVIDIA, Roberto Martin from University of Texas, and the session will be chaired by Nikolai.
Okay, let's get started. So this part of the workshop is meant to be interactive. That's your chance to talk with the speakers and challenge them on their views or agree with them. I'm going to kick off the discussion with some questions while people are thinking about what to ask or what to discuss. But I really hope that that's a place where the audience gets involved as well. So I'm going to start with a question for the panelists. We've been talking about integrating perception and planning and control and things like how to measure uncertainty and how to represent the environment. So my first question is to the panelists is, what challenges do you see in this idea of integrating perception and planning? Specifically, what do you think are some of the hard problems that we still don't have kind of principled solutions for, and we should look at in a more theoretical way rather than just look for ways of combining existing algorithms?
So I can say something with this. Okay, yeah. So, does it? Do you hear me now? Okay, great. Okay, so I mean, the first thing first, I think I agree with the premise of this question that integrating perception and planning is actually very important. And I also kind of showed you the experimental evidence for why that is very important. If we decouple perception from planning, we train them separately, or we design them separately, we are very far from the optimal behavior. One challenge that I'm not sure is that theoretical, but very practical in terms of developing a robot product that I see in autonomous driving, is that if we integrate a system, then we will have one thing, right? And it's very hard from there on to work on the different components independently, right? So that's kind of like something that I feel is a barrier in practice for these methods to have an integrated system. That means I can no longer develop it independently, cannot evaluate it independently, and so on. But at the same time, if I do evaluate things independently, then it's the gain I make in certain components oftentimes does not translate to the overall system improvement. But so I don't know if this answers the question, but this one thing.
Anyone want to add to what Peter said?
So you are advocating for your solution to integrate models?
In some sense not, but because even then, even if you integrate, even in this framework, right? The issue again is that now you coupled them, and now I cannot just improve my perception on its own. I need to do everything together, right?
So your question is, how do we combine kind of like modularity and end-to-end in a way that we can improve each of the models while still kind of
exactly, which I don't know if it's even possible.
So I have a different one, and it's about uncertainty representation. And you talked about that also in your talk, and it's something that is, to me, has been very frustrated, especially when it comes about representing uncertainty on geometry and space. We have models, they are kind of like finicky to use when you want to represent uncertainty about our orientation, things like that. When we go into the learned world that is giving so good results, it becomes even harder because, yeah, there are ways to incorporate uncertainty into learned models, but it's tricky and it's complex. And then there is the problem of when you want to reason about uncertainty, which is a big thing, perception is about reducing uncertainty. It becomes intractable very quickly if you try to do it in the way we know how to do it. So to me, we're somehow missing new ways of representing uncertainty, computing with uncertainty, and making decisions with uncertainty. That is basically, to me, the connection between perception, planning, and control is somehow where these three things kind of like get together.
I agree 100% with that. So from my perspective in manipulation, that's where I find the challenges when you're only looking at it through planning and perception. The uncertainties there make everything go wrong. So it's very important to account for those uncertainties, and that's where I am confident about the control part of it, which in some cases, and most we can kind of account, we can define that system and prove that it's stable against these uncertainties, wherever they may be. I had a question over the break on exactly that. Like they were asking me, why do you need to use a controller and don't use high-level planning? And you can, in grasping and manipulation, you can, there are so many planning algorithms where you need to know precisely where to position the fingers around the object to have a stable grasp. But that's not always possible, and there will always be errors. So you need that, even when that happens, it needs to be robust enough to account for any errors or uncertainties and achieve still that stability.
Yeah, so I'm not, this is working good. I'm not really a planning person, so for me, I see this as like a question of whether we need more theoretical guarantees. It feels like a lot of what humans do has no theoretical guarantees, and we manage to get along pretty well by being robust and adjusting as we go. So yeah, I feel like we need to really get good closed loop perceiving as you're acting, and the plan cannot be at the very lowest level because we never really know what's going on at the lowest level.
Any comments from the audience or feedback on what we heard so far? Or a new question? Okay, we have a shy audience. I can ask more while people are thinking about ideas.
One person there.
Do you mind going up to the microphone? Yeah, that would be great.
Microphones so can go around maybe deep.
Yeah, maybe we can. You can have one. Just yeah.
Can you hear me? I guess my question is a little related to what Peter was talking about earlier. When you're working with an integrated system, it's kind of hard to pull out one module and look at it. I'm curious what you guys think about similarly how to do like failure analysis or failure detection. When, from personal experience, when my integrated system fails, it's sometimes hard to kind of figure out where it fails and how failure at one level can cascade to failure at a different level. So I'm curious as to what you guys think about that, and also if you have techniques in terms of determining where your system fails and maybe how to debug it.
Yeah, this is all very related. So if you don't have a modular system, it's very difficult to make this kind of like isolated experiments to know where your system is failing. So we're moving towards more integrated modular end-to-end systems, and that makes it very difficult to introspect when something fails. Where is it failing? So yeah, that is one of the risks. We have seen the benefits of end-to-end, but one of the risks is that exactly. So how to deal with error analysis. I thought actually you were going in a different direction with your question about error. I thought about you were asking about how to integrate error detection in the agent itself. How the agent can actually be aware of its own errors, which was also what Kostas was asking, and yeah, basically kind of like integrate that as part of the perception planning control loop, which is also a very interesting question. But yeah, to your question, I think that is one of the risks of end-to-end modular systems. And I don't have a good answer. I guess, yeah, it depends if the benefits of having it end-to-end compensate for problems like that.
I can also say something, I guess, on this. On one hand, I think the errors are still somewhat easier to detect when we say that some model fails. Then what's more annoying is the soft failure, where it's just not good enough, and so this error propagates to the next one, and you know, it's not that easy to, even if you have a modular system, to you know, pinpoint what's wrong. Second thing is that even if you find something that is wrong, what do you do? And this is also what I see in developing autonomous vehicles. Modular systems sound great that I'm going to know which module fails. However, it takes enormous amount of effort to then like kind of do something about it, right? So you will have each module, you have to like then, you know, separately address them with different mechanisms to find you know, edge cases for each sub module, and then, you know, like, improve things. So in my mind, although it sounds a bit crazy, I guess, it could be that actually an end-to-end system that doesn't have any internal understanding could be more practical in that at least it only has one, you know, like one box, one way I need to address limitations of it. So say that I just need to collect more data around a certain behavior, and I do not need to worry about the internals, right? Because if I have the chance to worry about internals, I will end up worrying about the internals, and that's a lot of engineering effort. So if we could have a system that just, you know, consumes each sub data and improves, maybe that's a kind of like, you know, washes away the problem and a convenient solution.
Like something that right.
Exactly.
Yeah, it's something very similar, which is, yeah, in a system, if you have a failure, probably it's a data problem, and so you need to sort of propagate that to figure out what data you're missing, and then you can collect it. Unless it's an architecture problem and you're unable to represent that, I think, the data, and that's, I think, a harder problem to solve.
I'm gonna again talk about control, but I agree that it's a very difficult problem. When you have a really big integrated system, you never really know where the problems are. But at least for some of the modules, if there are theoretical guarantees where you know exactly where something should be working, and you somehow detect that module fails, you know, based on the assumptions that you made and the guarantees that you have, all the cases where it's not working, and that can help you understand where the problem was. But again, it's not, I don't have an answer for that either, so we can only just pick some cases and based on what we know and try to have some safeguards. And then another hand.
Thanks. I have actually a somewhat related question to what we were discussing before. I've always been a big fan of modular architecture, and I really like that we can train them also end-to-end tasks. But one thing we didn't really talk about is that we are also fundamentally limiting ourselves to the representations and the power and interfaces. Now that's a strength, but it's also a limit, right? And we can maybe fix it to some extent and thinking about uncertainties. Again, then we can think about how do we represent uncertainties. And these are not straight like the representations, they are fixed. So what do you make of this limitation? Do we think it's a problem? I think it might be, or what can we do about it?
What's that?
All right, I can give you my view. I think well, there's also representation learning as a kind of like a problem setup where you try to make flexible the representation itself. But it's true that it's always kind of like the easiest is in this modular setup to predefine these interfaces. And I think we're missing somehow sometimes in robotics a better understanding of that system building, of that how these interfaces actually affect. Sometimes we kind of like focus on our models or on the entire system, but how these design decisions kind of like influence the performance. That it could be that each of the models are perfect and your system is great end to end, but we are not factorizing the right way. And there's somewhat missing there a science of systems in robotics in a more proper and kind of like fundamental way that, it's not there. So we are all hand wavy, like, okay, let's put this interface here, the one that everyone uses. So it's that's my feeling. We're missing something there on how to properly explore that space.
Yeah, I can agree on that. The reason why I kind of like our research on these differentiable stacks is that in some sense it offers at least some way to choose between the two depending on like the designer's decision, right? So it doesn't answer your question of what we should choose, but at least it allows you to choose any one or the other in any part of the system, and the still kind of represented in a single formulation, right? And so it more like makes it a design decision. Do I want to learn this interface? If I want to, I can do it. If I want to specify it, I can still handcraft it and still do the learning. But it actually doesn't answer anything about which one should you do. And in fact, I really don't know.
I think it depends on the use case. So because some tasks, some things we want them to be very strict, to never falter, to always follow what they're supposed to be doing, and not be adaptable in any way. And in other cases, we want them to be very adaptable, very compliant. So we need to kind of learn these kind of uncertainties. But I don't know how we should have like an overall idea of what that would be. But depending on the case, I think you can make some kind of decisions.
I think that's a pretty critical aspect, the representation question, and I feel that it shows up in the end-to-end setting as well. Even if you have a huge neural network, you still choose the dimensions of the different layers in a way. So one related question I'm going to ask the panelists based on this is, do you feel that now that we're talking about representation, do you feel like that there should be some structure to those connections between the modules, or can it be just a high-dimensional vector? Because in robotics, unlike in computer vision, we have a lot of structure in representing environments. Like we use different sort of models for occupancy and for object shape and so on. Do you think that we can just map all of this to a high-dimensional vector, or is this structure somehow important, which has been hand-engineered so far? So how do we learn about structure, or is it something we can give up?
I mean, I think even before that, even with a large neural architecture, you're still making decisions about what you're putting in and what you're putting out, and the images, the portfolio, how you're representing all those, like all affect things at the time. Like we found, like just discretizing actions versus not discretizing actions makes huge difference, and there's no reason that it should, but for some reason it does, and I think there's still a lot that we need to explore there. So, what is the best way to do those things?
I have one question about the in-between network. I think it will be very hard to identify the common case in each case. Because the common case is a perception we learn the same from the So I think it will be very difficult to separate, and it will not be, and the problem will not be solved by bringing more data to the model, because when this endpoint approach you well, then becomes bigger, so very needed, more going on that happening. I think it will be not sort of a sort to identify this problem. So maybe even another we should expect to this spring.
I think it's also very difficult to get all the corner cases for hand-designed versions as well. And I guess there's just a finite amount of logic that you can encode into any visualized program. But one way that I'm pretty excited about in terms of finding corner cases for large models is using, if you can represent uncertainty in a useful way, and then actually have the agent search out for high uncertainty areas of the observation space, and then you get data that you need to learn those areas. I think it's logic setting in that direction.
And also maybe a comment on this. I agree that it's indeed very difficult to find corner cases, regardless of whether you have a structured representation or not. But something that maybe could help is if you do have some intermediate, representations that are interpretable, right, or have some auxiliary outputs that you can examine, and so you can have a chance to say that why is that my overall system failing, where does it need more data? Oh well, because it couldn't see that there is somebody on the road, so therefore, of course, the action was wrong. Yeah, maybe that's all.
How your plans were, how limiting do you think is the requirement of actual differentiable modules?
Okay, it's a bit closer to my question.
Can you hear me now?
Yeah.
Yeah, my question is like, how limiting do you think is the requirement of modules being differentiable for a complex system like autonomous driving? Because there are so many discrete happening, like a balance. So what do you think about that?
Yeah, I will quickly answer this. Yes, it is limiting in various ways. We have some methods to approximate gradients even for discrete or normally non-differential components, but there's a lot of issues around this. You have a large computation graph, doesn't fit into memory, gradients, variables, it's hard to learn from all that. So in some sense, we kind of could use much more suitable optimization methods that in fact can optimize even in that landscape. So yeah, maybe that's my answer. It is a bit, but also we can, if you think of it, not necessarily. I mean, I was kind of talking about this in this talk of something that we won't exactly follow the same algorithm, right? To say that, I want to have the exact same computation, I want to differentiate through it. But of course, in this whole kind of approach, you can have the choice of relaxing some part of that system, right? And if you find that maybe that component that we have is too hard to differentiate through, yet you want to do this during training, then you have the opportunity to relax it, say replace any part of that thing with a learned component.
Yeah, there's one more.
Thank you so much for answering all these questions. One of the things that I was curious about was at some point during the panel, we talked about how human reasoning, for example, doesn't have theoretical guarantees. The key thing here is how we relate. We're talking about integrated systems, how kind of we're also perceiving acting. And it's natural for us to relate that to how we do it as humans as well. When you're conducting your research or thinking about these ideas, how much is that? How much of that comes into play when you're reasoning about research direction? What's important for a specific problem that you solve? You think that things that we should be considering when conducting research, or are we trying to kind of go above and beyond? Maybe theoretical guarantees are useful for autonomy for these types of integrated systems.
Yeah, I think humans are always a good inspiration for trying to create intelligent behavior because it's the best example that we know so far. So yeah, I look at it as an inspiration, but we don't know. I don't know. I'm not a cognitive scientist, and I think even cognitive scientists have a lot of questions. So yeah, how to implement those ideas, how to implement those behaviors is something that diverges a lot. And there is where we have the possibility of opening the black box that is the human way of doing things and create ways that are more controllable with more guarantees, where we can kind of like reproduce things in a more systematic way because we have machines that are a little bit more under our control, at least so far until the robot apocalypse. But yeah, so that is my short answer. Inspiration, yes, but we don't need to replicate everything. We cannot replicate everything. We don't know how it works. So we can include the guarantees that we want, and we should try to include as many guarantees as we can keep.
I agree with that. It's, of course, the inspiration comes from humans, and that is something that I've thought about a lot because I'm working with robot hands. Do they really need to look like human hands? Do they really need to have 5 fingers or not? And the answer is both yes and no, because yes, because all of our world is built for human hands. We are living in this world, so everything is built for us to be able to have it. So in that regard, yes. But then again, no, because there might be some other ways that we haven't imagined yet. And a lot of scientists get inspiration from other biological beings like octopus and or usually soft robotics related to create these kind of creepers. But always when you try to implement it, you always need to have some sort of theoretical guarantees, because in the end it is an autonomous system that you need to make sure it's working as intended.
I think it also really depends on what you want the robot to do. Like a lot of cases of robotics have nothing to do with humans. Like we just want something to put the part in the right place as fast as possible, which humans are not very good at. But if you want something to be like a robot later, then you might want to be a lot more inspired by human interaction. But yeah, so I agree.
I think that's a good point to maybe thank our panelists. We are running a few minutes late, and I know everyone wants to get to lunch. We have about an hour lunch break, and we'll resume again at 1:30. So let's thank our panelists for their time.
So, welcome back, everyone. Our next presentation is from Changhyun from University of Minnesota. And the talk is about interactive robotic object perception and manipulation. So,
okay, yeah, thank you for the introduction. I'd like to start first with the title, because the title is a bit kind of too generic. So I'd like to explain a little bit more about that. So, from the title, you may guess that I'm going to talk about object perception using camera to recognize objects. And also, I'm going to talk a little bit about the manipulation, using kind of robotic manipulation to grasp object or doing some manipulation. But maybe some of you might have some question about why I put the interactive in the front of my title. So I actually noticed that the interaction between the perception and manipulation is actually kind of really important. So usually in robotics, we usually kind of use the perception to guide manipulation. But also, we can also use the manipulation to improve or facilitate perception. So I'm going to talk a little bit about that today. So I'm going to present two set of the topics. So first one is object searching and grasping, and the other one is object segmentation by manipulation. Okay. So first, I'd like to show the object searching and grasping. So the main idea of the object searching and grasping is basically just kind of finding the target object, even if the target object is kind of invisible or highly occluded. But if we actually look at how humans are actually kind of doing that, is really amazing, because we do have some kind of notion about the target object, but also we have we use our manipulator to search it through, even if that is actually kind of invisible. And it's a really challenging problem for both perception and the manipulation, because usually the scene is very occluded. Well, there are a lot of clutter. The scene is a really highly cluttered environment. And also kind of making decision on this kind of thing, cluttered environment is very challenging. But we noticed that humans are actually pretty good at it. So we actually asked the question that how do we enable robots to perform this kind of human level searching and grasping capability? So we are not the only one who actually solved the problem. Actually, it does have a long history. So a long time ago, Du et al. Tried to use both pushing and grasping with a focus on planning. But at that time, they used some kind of the pose estimation using some prior 3D model. So it was a bit limited to apply for more novel objects. Chang et al. Tried to combine pushing and grasping, but the main focus was target agnostic grasping, meaning that, well, doesn't really care which object it is, just grasp one by one. Okay. Fang et al. Solved the target-oriented grasping, so finding some specific object from the scene, but as you can see, the scene is pretty sparse, so it's in terms of perception and manipulation, it's a bit easier. Mechanical search by the Daniels et al. They solved the problem, tried to solve the similar problem using grasping, pushing, and suction actions. They formulate it as a POMDP, partial observable macro decision process, but it's really hard to solve the problem, so they had to rely on some heuristics. As a result, some action was kind of suboptimal. So the identified challenges was that here, even if the object is maybe initially highly occluded or even invisible, then how robot can actually search through it. And also, even if the object is visible, then how robot can actually make a decision to do the grasping successfully. So we formulate the problem as a macro decision process, but the original problem here is really challenging to solve. So we divide into two parts. When object is visible, then the problem is a bit more like kind of how to combine the multiple manipulation tasks, like using pushing and grasping, and also how to train the robots to decide when to push and when to grasp, depending on the situation. But if the object is kind of invisible, then it's more like searching problem, right? And we call that exploration, while the grasping the visible object is called coordination, because we need to coordinate between pushing and grasping actions. So let me walk you through the pipeline. So we do have the 7 degrees of freedom over arm, and we have one RGB camera looking down the table and where there are multiple objects. Okay. So from the RGBD camera, we first observe the scene, RGBD scene, and from there we first run object segmentation to detect whether there is a non-object segment or not. And also we do the projection so that it can kind of convert to the height map. So as if we can see from the top. Okay. So from the height map, we learn to convert to QNets. We use the DQ network for training. So here the critic network is basically object accepting RGB depth and object mass that is perceived from the object segmentation model. Okay. So going through this convolution neural network encoder and the two separate decoders, so we managed to find this QMass. Okay. So we follow the standard DQ network, but we found that it's not really easy to train in this case because depending on the task, difficulty of the task, some Q values actually is really imbalanced. As you may know, here the Q value actually represents expected return if you apply the action. So here Q map actually represents each pixel represents the Q values. So usually we pick the highest Q values to maximize reward. But because here the pushing action is much easier to train compared to the grasping action, usually there the Q value is actually imbalanced, meaning that if you just always pick the highest value, it may keep just the pushing rather than grasping. So in order to really handle that, we have to train additional policies, two separate policies. Explorer for exploration, basically just using pushing actions to discover the initially hidden object. And the coordinator does coordination between pushing and grasping, so that it will facilitate the grasping at the end. So one of the design choices we did a bit carefully was actually real design, real function design. So especially when these really sparsely worked tasks, learning is very, very hard. It requires a lot of experience. So we had to define the two different reward function, post-action or pre-action. So post-action is basically after the action, if the result is really desirable. So in this case, pushing action, we like robots to make some more space for the future grasping. But even if the action wasn't really successful, but as much as the action was the title of the target object, then we still assign some small reward. And that actually made the learning much faster and more effective. Okay. And also we did the same thing for grasping. As much as the grasping was a title of the target object, then we gave some small reward, but it was actually successful, then we assigned high rewards. So we first trained in simulation with those some non-objects. So here the goal is to grasp those colored objects. Those are target objects with some fixed sequence. So as you can see, as we increase the training iteration, it gets better, right? And even if the object is not really readily graspable, it actually managed to break the configuration to eventually grasp it. Well, for evaluation, we first test on the exploration subtask. Again, that is the goal is to find the target object. So here usually it's kind of invisible, but robot is kind of doing searching motion using pushing action, and they eventually just find the target object. And also we test the coordination subtask. The goal is, well, even the object is visible, still the robot needs to make some space in order to successfully grasp the color objects. And according to the quantitative evaluation, we did some adolescent study with some combination of our model, and it turned out that our explorer actually managed to find the target with more than 90% success rate and the fewer number of motions, meaning that not only is more accurate, but also more efficient, because it usually kind of 2.7 motions, pushing motions. For the coordination subtask, we defined a different kind of the task cases, and we compared with some random policy and also some visual pushing and grasping method, because it's more like target agnostic, so we have to give some object mass to give the clue about which object should act on. And also we showed some order heuristics, some kind of heuristic method, and from our comparison, well, our coordinator actually achieved the highest success rate, again with a fewer number of motions. And we combine this exploration and coordination, and we did this experiment on real robots. Okay, so some of the objects actually trained one in simulation, and some of the objects are not trained in simulation, but we have to provide some pre-trained object segmentation model. And then we combine both, we evaluate both coordination and the exploration part. And the overall, the success rate was ours actually shows the high success rate, and again, fewer number of motions. So let me show a video, demo video. So here the entire screen is actually the input to the robot. That's what actual robot sees. And the side view, the upper left corner, shows the different view for the segment visualization. So first the robot just, because it doesn't see the target object, it kind of push with the hope that it will find the target object. And after some two further exploration, third exploration, it actually kind of managed to find the target object. And then eventually it was a kind of vision about how to cross. Okay. The second time here, the target object is mislinear, for example. So luckily it found the target object at one pushing action. And then also kind of reason about how to grasp it. So here, please note that, well, although the object is somewhat not really completely singulated, still we managed to find the good grasping pose. And this is for the novel object, so it's not really trained in simulation, but still kind of like readily applicable to the real world scenario. But of course, we have to train the semantic segmentation model again, and then it was a big kind of limitation. So the major limitation of our prior work was that we had to use the pre-trained object segmentation model. That means if we want to apply to the novel object, then maybe we may need to also collect more data, and we have to retrain it, and then we have to deploy the semantic segmentation model. So that's very inconvenient. Okay. So we asked the question then, how to enable robots to generalize to novel objects? Okay. So here, for example, if we just provide one reference image, and then the robot can actually look for the correct object. But maybe it may have a similar color, similar shape object in the background for the different object. So it might be a bit kind of challenging to figure out which one is which. Okay. So to achieve this one, we solved the one-shot learning for mobile object matching. So here the main idea is that we have the target image provided by the human, and then we first run the object segmentation from the IPPC, and then we obtain those like segmented objects. Okay. And then through the visual importer, then we convert the original image to the kind of lower dimensional length feature. And we convert first the segment and then concatenate with this test target object feature. And then the concatenated feature is actually going to the relational network, basically to calculate the distance between this target image and then the overall segmented image. Okay. So the main idea about the relational network is that instead of using kind of predefined distance metric like Euclidean distance or cosine similarity, we can use this similarity using more like a data-driven way. Okay. So as a result, then we can convert to the similarity image. Basically, just tell that the kind of the matching form. So here the yellowish region is the highest region, but we may have also have some kind of the lower possible regions depending on the kind of the visual appearance. So then with this kind of the network, then we replaced our previous pipeline a bit. So we call that as IOSD, image-driven object search and grasping. So the main idea is now providing this similarity image instead of the using the binary object mask. We provide both similarity and also RGB and depth, and then encoder actually import and also decoder generated Q maps for pushing and grasping. Okay. But now the another challenge is this similarity image is not anymore the clean object mask, because it might be kind of represent uncertainty about the matching between the target image and the object in the scene. So before it was pretty easy. It was pretty easy because we can just run the explorer if there was no target object, and if there was object, then we can run the coordinator sub policy. But now we have to train another policy, basically that's just to determine that whether it should run the explorer and coordinator depending on the similarity image. So we simulate, we train in simulation, so we know the ground truth. So we train this one is more like a supervised method. So this video shows that here upper right corner shows the only reference image corresponding to the target object. And then you may see that there are some kind of similar objects, similar color, similar shape. But even so, the robotics managed to find the target object probably discovered by those like similar object backgrounds. So if you're interested in to know more, then this paper will be presented tomorrow in the perception and grasping and manipulation 2 session. So please check that out. So now I'd like to talk a little bit about the object segmentation by manipulation. So the main idea is that can we use the robotic manipulation to improve the object segmentation model? Okay. So, well, in order to kind of motivate you, I'd like to ask one question. So this is a video from the BBC and showing the cuttlefish. But can you find a cuttlefish in this snapshot? Well, cuttlefish is actually, as you may know, it does have really nice, very amazing camouflage capabilities. So it's very hard to really distinguish the cuttlefish from this scene. But if you take into account motion, then you can actually have a better sense about what is this segment, where is the cuttlefish, right? Which is actually floating in the middle of the ocean. Right? So inspired by that, well, we thought that maybe it might be impossible to have a perfect object segmentation model as long as we only have one snapshot. Okay? So, well, even if we have a really gigantic neural network with a massive amount of data, still maybe there might be some kind of edge cases like this kind of rabbit, snow, and so like butterfly very has a similar texture. So instead, we are kind of like intrigued by how humans actually learn something, especially the human infants. For the infants, actually, most of the objects are actually novel objects. So they are pretty curious about that. They try to kind of reach to it and they try to grasp it, try to look at it in a different viewpoint. And by doing that, they have a better sense about the object segments, to get familiar more about the object. So the key question we asked was maybe how to enable robots to improve their segmentation capability for novel objects. Okay. So here's the main idea. So we gave a set of the novel object to the robot. And then we let the robots interact with those objects. Okay. And well, you can see that here, the object does have some textures. So if you just run the off-the-shelf object segmentation model, it may not really have really clean segments. Maybe it may have some under segment or over segment. But by just kind of interact with it, it does have a more sense about the kind of the information or the information about the object segments. So specifically, we train SH policy. This is a short name for singulation and grasping policy. Here, singulation is done by pushing action, and the grasping is done by grasping action, of course. And then by doing that, well, first the robot spread the object out, and then look at the image before and after the action, and also do the same thing for the grasping. So from that, we can actually obtain some kind of pseudo object mass, more like ground truth level, and maybe from optical flow. So based on the motion, we can actually then have a confidence about the segment. And then once we have enough data, then we can actually fine-tune off-the-shelf segmentation model. Okay. So of course, after that, we have a better segmentation results. So that's the idea. So that's actually the detailed pipeline. Of course, I'm not going to go into detail. So I'd like to just briefly mention that we have some off-the-shelf segmentation model, and then we first have initial segmentation here. Maybe pretty noisy, especially the segmentation model is not trained on the set of objects, but still we provide that kind of mass image and also provide some mostly cluttered object mass. We do hope that that will contribute to or give some clue for more effective simulation action. And then it goes through the conversion layers and the decoder. We generate those push and grasp payments. So we first train the object singulation. In order to give the reward, we define the graph structure where the center location of each object is more like a node. and the objects are close each other, then we establish an edge. And here the goal is to kind of decrease the density of the graph. So initially it might be very close to the fully connected graph, and later it might be going to the more like zero. So as well as the action actually resulting kind of decrease the density of the graph, then it gets the positive reward. And the first, well, once objects are spread out, then grasping is much easier. So we also learned a more typical way, and then we obtained the training labels with some additional processing. And then once we obtain those like training data, especially here, we show that this video shows how we train simulation in simulation. And then once we obtain it, then we so here we combine, first we train separately and then we combine together so once we train separately and then we join to train again. And then, so we use the additional data for fine-tuning the off-the-shelf segmentation model. So long story short, so we achieve the high average precision compared to some baseline, some state-of-the-art baseline. And also we apply to the real robots. And then that also shows that it does have a better accuracy. So from the kind of the additional data from the manipulation. Okay. So to summarize, well, I noticed that the interaction between perception and manipulation. Okay. For example, here the object structure and grasping, the manipulation action, the explorer and the coordinator change the environment so that you can find the target object. And once you find the target object, that perception helps the manipulation. And for the object segmentation by manipulation action, generate additional data so that it can improve its segmentation model, and also improve the segmentation model also at a more accurate segmentation measure that also kind of guide a more accurate perception. Sorry, accurate manipulation. Okay, so yeah, that's all for today. I'd like to thank to my students who contributed to the project, and also thank my funding source. Thank you.
Thank you, Changhyun. Any questions?
Thanks for the talk. So for the first part of the work, what's perhaps some physical constraints for the manipulation? Perhaps, you have a relay environment, we don't want to throw things around while we push them, or it could be a very large file, and as you try to push things around, then you make it unstable. How does this apply?
Yeah, the access space is basically, well, it's more like the top-down manipulation action. Here, the pushing action is just more like, well, typical pushing, and grasping or the kind of top-down grasping. So we assume that the objects are actually kind of on the table, but it could be also in the bin. But in that case, we need to think about the collision of the kind of bin or something like that. But we didn't really consider that yet. But yeah, so the action is it did actually kind of change the environment, but it's not really significant change in the environment. So in that sense, I would say kind of, yeah, it's kind of reasonable in this setting. But of course, well, we can actually go a bit more kind of the realistic side if we consider like logistics environment, something. Thank you.
Any questions?
If there are no more questions, let's thank our speaker again. Okay, the next talk we have is by Coline Devin. She works at Google DeepMind, and she will tell us about transformer-based policies for multitask manipulation. And her work has been focusing on using data, even if it's not robot specific or task specific.
All right. Hi, everyone. My name is Coline Devin. I'm a research scientist at Google DeepMind. And I'm going to talk about some work that we've been doing in the Google DeepMind Robotics group. I made my title a little bit more spicy by adding the towards more general robots. And let's see where that takes us. And to start off with, this is work that was done by a very large number of people that were all working on this from different directions. And then we're kind of merged into one group recently. So I want to thank all of these people for the amazing work. And I personally did not touch every single piece that I'm going to talk about, but I want to represent what they've done. So I think one common goal that a lot of us here have is that we would like robots to be better generalist agents, which would look like understanding visual and language instructions, being able to do some grounded reasoning about the world, perform any task if you give it enough supervision, and improve on their own and share knowledge to other robots. We're nowhere near this yet, but I want to highlight a bit of work that's been on this journey towards getting more general. So SayCan was a work from Google that used a language model as a planner and then looked at a learning and affordance function to kind of choose this. And this looks as using a language model as planning for robotics. I have too many videos in this slideshow, so it becomes very slow. Then RT1 took this transformer idea and trained it directly on robot data to be able to perform many more tasks. We have Palmy, which uses a vision language model pre-trained to do planning, but then co-trained with grounded robot data to get even better results. RoboCat directly trains a single model to be multi-embodiment and to fine-tune easily to new tasks. And RT2 takes a large VLM as a robot policy directly to generalize to new tasks and show chain of thought reasoning. So what we've kind of found is that to get more general robots, we need to learn both what needs to be done and how to do it. And pre-trained language models can give a pretty good guess about what needs to be done. And this is a very old example, but like GPT-3 could already tell us that maybe we need to use a vacuum cleaner to spill a drink. Maybe that's not a very good guess, but we can imagine that it could be better. And given that someone tells you what you need to do, the robot also needs to know how to do it. So this is from the SayCan work where the language model was providing a very broad plan of what to do to spill the drink. Maybe find something to clean it, go find the apple. These are all guesses. Some of them are good, some of them are bad. And then the robot can go in and weigh each instruction by how likely it is to be able to actually be accomplished. So the robot knows what it can do. It knows that it can find a sponge, but it doesn't know how to find a cleaner. And so we can just adjust that plan based on the weights the robot gives. But then how do we actually learn what to do? We collected a very large data set of language conditioned teleoperated demonstrations, which provides a good grounding of teaching the robot how to perform lots of different subtasks, like pick up the Coke can or move the chips to the drawer. And then if we just train a model on this, we get a language conditioned model. And we found that using a nice transformer network gets really good results when you train on that data. And here the instructions are just tokenized like language. The images are tokenized and the actions are discretized. And so you output tokens. And so it all kind of fits well with the language modeling paradigm. And this was 35 million parameters, which was very large in some sense, but now also feels very small, depending on where you're looking at this from. And so if we take the policy that we've learned from language and images to actions and combine it with a large language model that provides you with a plan of what actions you should do when, what tasks you should solve when, we can get nice long horizon changed behavior of the language model saying, first find the sponge, then go to the mess, then clean it up. And the RT1 model, it knows how to do all those sub little language instructions, and it can then actually output the actions. But so that was all just using the language model as is, no additional training. It was already pretty good, but it doesn't know anything about robots. So there's really kind of a wall you hit when you try to use that. So instead of just using it pre-trained, maybe we should co-train it with the robot data as well. So PaLM was a language model, large language model that was trained for looking at images and answering questions about them. And we can take that model and fine tune it with the robot data. So we have robot data that we've labeled as like, given this image and the robot state, how to grasp the blue block. And we can train it to answer first grasp the yellow block, then grasp the green block, depending on what was in the image. And so if we do that, then we can get much more reasonable plans out of it. And then we can use something like RT1 directly to control the robot. So this separates out the control and the language model, and the interface here is just language because RT1 was trained to take in a language as input. So how this looks is that we can also do this with multiple embodiments. So the language model doesn't care what the embodiment is, it just gets images, it gets language, it outputs language. And then we can have different control units for each of the different robots that were from prior work. And we see something nice, which is that we can do this closed loop end-to-end planning to do longer tasks. The important thing, though, is that we trained it with the language and the robot together. So we can see that the multi-embodiment aspect really helps here. So if we take the model and we just fine-tune it towards a single robot environment at a time, it doesn't do so well. But if we train it on everything, on the robots, as well as with the language and vision data, we get much better results across the different environments. So here we have the language model that just gives language plans, and then we have other models that take in language and output actions, which can be a little annoying if we want to do something more complicated. So we could just output directly actions. The pre-trained models, the large language models, they're trained to take in tokens and output tokens. And those tokens are usually from a string or from an image. So if we want to modify the robot data to be able to go into these models, we can make some small changes. So we take our robot actions and kind of change them into, we discretize them into 256 bins. So instead, we convert this to a string of numbers. So the model is already trained to take in strings that contain numbers, like on the internet. There are people talking about numbers. And so we can actually just take the numbers in our robot action and give them to the model as if it was a string of a number. And this sounds a bit silly, but it actually does work pretty well. And the model already has some sense of like what numbers mean. It probably knows that 10 is a larger number than 1. So it's not entirely unreasonable. And so if we do this, we train with our robot data and our language data, and we fine tune together, then we get a nice model. So the way it works at inference time is we convert our robot task into a sort of vision and language task, like what should the robot do in this image in order to do some task, and then the model takes in all these tokenized inputs, outputs a string of numbers that we know is an action, and then we detokenize it and run the action. So if we compare this to the RT1 model, trained on the same set of tasks, on the tasks that were seen during training, the RT1 in red is quite similar to the RT2 models. But on the tasks, if we evaluate on unseen tasks, we see much more generalization from the RT2 model because it's seen all this previous web skill data about questions, asking questions about images, and just general language reasoning. So we can generalize better to unseen objects, unseen backgrounds, unseen environments. So this is really a generalization benefit. We also can compare whether we should fine-tune with only the robot data or fine-tune with the language data as well. So that's blue versus green. We see a bit of a benefit from keeping that language data in when we're training on the robot data. We see a nice scaling factor. So if we train a small model, 5 billion, this is a large model, 55 billion. Now, of course, this gets expensive, and we are hitting the limits in terms of how fast we can run inference on these models to control the robot. So there's a limit to how big we can go if we want to actually run on the real robot. But there's kind of a funny thing that happens with these models is that because of all this like language knowledge inside the model, we can ask for tasks that look very different from the training task at the instruction level. The behavior is very similar. But for example, we might have asked it to put an orange in the bowl, but at test time, we can ask it to put the orange in the matching bowl. And the model figures out that one bowl has an orange in it already, and the other bowl has apples. So it puts the orange into the bowl that has oranges in it. And we don't have any robot data directly following that instruction, or pick up the land animal. We never told the robot specifically what a land animal is, but because that information is all in that language and vision data that we're training with, it generalizes that knowledge. So we're getting robots that can be a little bit more general about their reasoning about the world, understand language instructions. We found that if we collect a bunch of data, how to perform a task, it does in fact perform that task, which is nice. We can just make bigger models. They keep performing tasks if we give them data. But we haven't seen them improve on their own yet. And that's a bit sad. And improve on their own, to me, usually I would think of reinforcement learning, where we have a reward function and the robot iterates and tries. But reinforcement learning is hard, and it's hard enough in the single task setting. In the multitask setting, it becomes a lot harder, and it requires having reward functions. So I'm going to talk about a little bit of a different way to think about improving on your own and sharing knowledge with other robots. That looks like, if you squint at it, it's kind of like RL, but it's a very slow version of it. So we have this project called RoboCat, where we want to train a multitask, multi-embodiment agent. And here it's goal conditioned instead of language conditioned, which is a small difference. But we wanted to be able to continuously improve. And the way we've thought about how to continuously improve is if we take our general agent, a general agent should be really good at fine-tuning to new tasks, given a small amount of new demonstrations. So we collect new demonstrations on a new task, which should be small, should be fast, and then we fine-tune our agent to that, and we should be able to perform it really well. So now we have a specialized agent, and then a general agent that doesn't know how to perform this new task. So we use our specialized agent to collect new data on this new task that we have, and this is now the robot just on its own collecting a bunch of data on this new task. And then we can take that data, put it back into our large training set, and retrain a large stimulus model that now has an additional task that it can perform. And so this model is based on the Gato model, which thinks about just taking lots of data from lots of different domains and tokenizing all of them so that they look like language, and training one transformer model that takes those tokens as input and outputs the actions as tokens as well. So there's no embodiment restrictions, because we can just output more actions token if we need to, or input more state tokens as needed. It's all just a big sequence modeling problem. And it's vision-based. We have pixels in, actions out, and here we have like visual goals that tell you what tasks to perform. The visual goals are nice because we can train on any data, because all trajectories are successful at reaching the state that they did reach. So we can use this hindsight labeling approach to train on unsuccessful data as well as successful data. In order to bootstrap our generalists, we need to actually start with quite a bit of data to get something that's good at fine-tuning to new tasks. And this data comes from mostly in simulation, where we just train an expert in sim, get a bunch of rollouts of data. We also have some real-world tasks. We have teleoperators to collect data in the real world. And this set of data is what we use to train our first iteration. And then for our second iteration, we have this additional data that was generated by the robot agent after it was fine-tuned on those tasks. And we have multiple embodiments where we have in sim and in real that are even have different control frequencies. And this we just put it all into the network and train it. And it comes out working pretty well. And then we also take our agent and fine tune it to new tasks and get 13 more tasks and even a new embodiment that's a 3-fingered hand that has 14 degrees of freedom. And so the process for adding a new task is that we ask for our set operators to collect 500 demonstrations of our new task, fine tune to it, and then we then collect data from those new tasks. So we find that and we do this for tasks that are both either the same embodiment and objects or different tasks. So for example, we've seen some of the objects in training, and then we learn a new task like putting them into the bowl, or different objects and tasks like this shape matching cubes, and then even a different embodiment. So this gives us a whole loop where we can, in theory, continuously improve our agent. And what we hoped for turned out to be true, which is that if we take our first iteration that didn't include a number of tasks in it, and our last agent that had more tasks in it, even on the tasks that were seen by the initial agent, the final version performs better. So we got transfer on previously seen tasks with new tasks that actually don't match those initial tasks. So it's a nice sharing of performance. And also the most important thing is that our new agent that's on more tasks is indeed better at fine tuning to even newer tasks. So a more general agent learns more tasks. And so we can, in theory, keep increasing at an increasing rate if this continued for more iterations. Thank you for listening. The recap is that we've talked about how to use language models as planners, training multitask language conditions, multitask goal conditioning, self-improvement, getting transfer benefits from language. So lots of cool things, but there's still a lot of things missing. Obviously, these models are not super precise yet. We're trying to get more dexterous tasks in. We're trying to get RL in to get much higher performance at the 90% compared to the 70%. And I'd like to see more mobility. This was all manipulation. So I'm looking forward to any questions you have, or if you want to chat about something else, catch me later. Thank you.
We have time for questions.
Thanks for the talk. If I heard correctly, you said 500 demonstrations for new tasks. Do you see a pathway to get it down as it keeps improving to 1 or 0? Perhaps just the higher level description of the task?
Yeah, it really depends on how similar it is to the previous tasks that we're seeing. So for example, we've seen for tasks that were just one thing had changed, we could do 10. But if it's something very different, then you need more. It's just like a kind of a continuous spectrum. So I suspect that as the model gets more and more general and sees more and more tasks, things are much closer in sort of the space of tasks, and so you will need fewer demonstrations.
You believe this is monotonic? Right?
Yeah.
There is no point that doesn't.
Well, at some point you hit capacity limits if you don't make your model bigger as well.
Thank you for the presentation. Actually, I have a question about this about YouTube.
Yeah.
So about could you share an idea or thought about this? How to choose the numbers or the entries?
So there's kind of two schools of thought, which is that you can either look for the token space, which is not used by the rest of the data. So some very infrequent tokenizations in the language, and just stick all your actions in there. And those haven't been trained at all by the previous data. Or you can just if your action was 3,2, you just use 3 and 2 as the like characters and tokenize them.
Thanks for the talk, it was great. I was wondering, since you showed the initial versus final RoboCat, did you have any like scaling law in general? Did you see any diminishing returns at all? I know you mentioned that it kind of runs out when you run out of low capacity, but I'm curious to see whether in the task type that you specified, whether there seemed to be some sort of diminishing return there.
So we only managed to do like one full iteration. So we need to keep working on that to see how it keeps going, but definitely we started hitting model capacities. So like if we use the version we were using, it was 1.2 billion parameters, but if we went with 400, like everything was worse. And I suspect we could go even bigger.
Thanks. So you mentioned you like to accomplish more precise and express tasks. What are future directions of time responsive beyond just collecting everybody data?
I think that for those, it's often really hard to teleoperate that kind of dexterous behavior, especially if we want to use like our new embodiment, this like 3-fingered hand. Very hard to teleoperate. So this is where I'm hoping for RL to help out. That we could train a specialist to actually do the test well and then use that data. But yeah, the problem right now is actually getting that data is difficult.
We have time maybe for 1 or 2 more questions.
Thanks again for the talk. Very, very interesting. Question: how much data does the system need to have about the environment? Like, we're expecting you to pick a robot and drop it in an environment, something like put it has to look around to find a sponge. How much context you need to do to give for that sponge might be? Is it capable already of exploring the environment, like driving actively the robot to look around? Right?
For the second part, not really. That's, I think, work to be done. Right now, we haven't been really getting the benefits of the mobile manipulation platform fully. I think that's definitely a very interesting area of research. In terms of how much data, I mean, that model, for example, was trained on about 100,000 trajectories over all the tasks. I think it's like on the order of 1,000, 10,000s that like, if you have a large model like that, you definitely do need quite a bit of data, at least at the base. Yeah.
Questions?
Last question. Yeah.
I have a question for the RoboCat. Part of the planner requires you that you have the robot to collect data, right? And I imagine that we can pass the noise. Your robot only is only showing very limited data for the new task. So does your method requires a way to determine whether your new data, like your demonstration, is successful execution or not?
Yes. So we actually combine that work with some other colleagues were working on doing success prediction, like trying to predict reward models. And so what they were doing is having labeling data with just a quick like sketch of the reward over the time. So basically someone just kind of writes when the task becomes successful. And then we just train like a simple model from the image to predict the task success. And it's not 100% successful, but it is good enough to grossly sort into successful and unsuccessful trajectories. And so then we use that to decide how to train on that self-generated data. But yeah, being able to label the success is very useful. And so we did it with this line method.
All right, let's thank Coline again for a great presentation and for answering so many questions. No, he's okay. He's connected to that. Okay. All right. Hi, everyone. Thank you for coming back. We're going to proceed with the next stop. It's my great pleasure to introduce Hyeonbeom Lee from Ajo University. Hyeonbeom is gonna tell us about autonomous navigation of outdoor mobile robots using monocular depth estimation.
Yeah, thank you. I'm Hyeonbeom Lee, and from now on, I want to share about my research, including the autonomous navigation of the outdoor mobile robots. So this is my content. Today, I want to mainly talk about the the sidewalk navigation and also for the navigation on the bad weather by exploiting the monocular depth estimation. So this is introduction. As you know, we can see the smart robots. So the smart robots are everywhere. So for example, the drones or the ground mobile robot can deliver the food for us. And also the big companies such as the Samsung or the Tesla, they developed the mobile manipulator or the humanoid robot that can help the human works instead. Key technology of these mobile robots are the autonomous navigation technology. So then what is the difficulties when we develop the autonomous navigation of the mobile robots? Let's think about these issues. So this is the difficulties for the autonomous mobile robot. So think about the indoor or the outdoor mobile robot fail to recognize the drivable area. Then the mobile robot may fail on the escalators or the elevators. Then they may hit the humans. Then that will be the very big issues. And also for the mobile robot, it's very difficult to cross the street because the humans or the vehicles don't want to wait the mobile robot. However, for the autonomous vehicle, as you know, they can equip the communication system so they can receive the traffic signal instead by using the communication system. So, however, the mobile robot cannot equip the V2X system or the communication system, so the mobile robot is very more difficult to understand crossing the work. And also navigation on the sidewalk is not easy because the sidewalk is more narrower than the road, and the learning on the sidewalk requires more accurate SLAM or the computer vision technologies. And also there are other difficulties for the autonomous mobile robot, according to the strict law regulations. I'm not sure about the US cases, but in Korea, according to the strict law regulations, one person must follow the robot when the robot delivers the food. So it's very funny, right? And also in the rainy weather, the robots are also difficult to move on the heavy rainy when the demand for the delivery robots are the highest. So it's a very big problem of the outdoor mobile robot cases on the bad weathers. So my research to resolve aforementioned problems, I want to propose the all-day navigation system using the autonomous mobile robot on the sidewalk navigations. So my strategy to develop the autonomous mobile robot on the sidewalk is that I want to exploit the edge map techniques exploited by the autonomous vehicle technology. Then I also want to develop the deep depth estimation for the handling the bad weather situations. So my approach can be categorized into the two parts. The first part is about the accurate sidewalk navigation, and the second part is about the depth estimation using the monocular camera. And the first part, we want to develop the edge map generations or the navigation using the hardware, and that are mainly related to the hardware developments. And the second part is about handling the bad weather situation. So we want to develop the deep depth estimation, and we want to validate our proposed algorithms. So the first part about the accurate sidewalk. So for the future delivery and the work, and many details things are proposed. Many details are in listed papers. So think about the simple situation that the mobile robot follow the sidewalk. However, unfortunately, the sidewalk detection is not easy. So the only works on the sidewalk detection developed it based on the computer vision technology using the stereo matching or the picture extraction. And to improve the accuracy of the sidewalk detections, so some researchers proposed the deep learning-based image segmentation with a sparse semantic point cloud, and that algorithm is proposed in the IROS 2020. And as you see in the center figure, so by exploiting the sparse semantic point cloud on the LiDAR, then we can get a more clear segmented result. However, unfortunately, if the dynamic obstacles are on the sidewalk, on the road, then the deep learning technology, the performance for the deep learning technology will be bad. So to resolve these issues, recently, many researchers proposed the end-to-end network via the simultaneous repairment. And as you see in this third figure, even the human are on the road or the sidewalk, so the segmentation can be performed very well. However, as you know, unfortunately, this kind of technology, including the computer vision technology, exploiting the picture-based information or the deep learning technology based on the learning, does not guarantee the 100%. So in that case, the mobile robot may invade the road while following the sidewalk situations. So before that, I want to see the real things on the deep learning technology. For example, the drivable area using the open source test. So we do the open source test using the this kind of as you see in the website. So in this website, the images the network are trained using the AI hub sidewalking images of about the 38,000 images, and they exploited the PSNet and the UNet. And as you see here, the UNet is a little bit old-fashioned deep learning technology, so the performance will be bad, I think. But as you see here, this is the test result. So as you see here, the test data, which is different from the learning environment, is not well performed. And as you see here, the segmentation between the trees or the road can be segmentation is little bit good enough, but the segmentation between the sidewalk and the road is very difficult to distinguish even in the deep learning technologies. So finding the drivable area in the indoor or outdoor mobile robot is a little bit difficult. Then let's first think about the drivable area for the indoor mobile robots. So let's think about the simple situations that the mobile robot explore the cluttered environment. So in this case, the cluttered environment include the furnitures or the chairs or the under the desk. So for indoor mobile robots, so maybe the under the desk is not the drivable area. So to overcome these issues, I proposed the new exploration algorithm by the 2D map segmentation and object detection, and that paper is proposed in the IEEE RAL in 2020. And my major contribution about this paper is that we want to find the feasible exploration path by detecting the obstacle for both the classified object or the unclassified object. And as you see here, in some cases, the mobile robot can understand what it is. For example, the chair, as you see here. But unfortunately, due to the specific pose of the camera, because mainly the camera is equipped in the bottom side, so it's very difficult to understand the big size of the desk. So in that case, we cannot find the feasible path for this kind of the desk situation. So our main contribution is that we want to by exploiting the 2D laser scan point and the RGBD segmentation, then we can find the segmentation here, then we can find the feasible area for the indoor scenarios. Then let's think about the outdoor cases. In the indoor cases, the object detection performance and the accuracy is good enough, I think. But the outdoor scenarios, there is many things to be considered. As you see here, there are in the outdoor or the urban scenarios, there are various elements in the urban environment exist for the autonomous vehicles. For example, we have the lanes or the traffic signs or the traffic lights or the lane boundary or the road geometry are the many things to be distinguished. However, as you see here, the traffic signs or the traffic light can be received by the communication system using the VTX. So the vehicle can understand what the traffic sign is. And also on the vehicle, we can have to understand where is the lane is and where is the lane boundary of the road geometry. So for the autonomous vehicle, they use the H map, so-called as the high definition map, do not using the detection of do not use the segmentation results. So I want to use the same technology using the H map for the mobile robot. So let's think about how car recognize the road. So as I said before, they use the HD map technology. So the H map is one of the essential elements for the autonomous navigation in the specific area. And H map contains the road information such as lane boundary or the center lines or waypoint with a specific direction and the stop line. As you see in the right figure, so the H map contains as you see here, the lanes or the direction of the road, or where is the lane boundary, or there is some stop lines here. So we want to use the H map for the mobile robot. Why? For me, I want to consider the mobile robot for the delivery robot cases, or the mobile robot runs on the urban scenario, then the delivery robot or the mobile robot always use some certain route. So because of this issue, I want to do the same thing for the autonomous vehicle technologies. So this is the step for the how to generate the edge map. As you see here, the generating the edge map requires a lot of time. And edge map also required, or edge map is generated based on the LiDAR SLAM on the point cloud. However, one of the major disadvantage of the edge map is that we have to draw manually by hand and by comparing the satellite images and the point cloud as you see in the pictures. However, once you draw the edge map, there is no problem with the recognition of the specific spaces. And as you know, for the segmentation or the sidewalk detection or the road detection, it also required the data set generation for the sidewalk segmentation. So the edge map generation also required many manual work, or the data set generation for the sidewalk generation also required the manual work. So in my opinion, it's the same thing. So generating the edge map is not the hard work, in my opinion. So I want to generate the edge map for the mobile robot. So to obtain the edge map, we have to compare the state-of-art LiDAR inertial SLAM technology, including the Rohan or the Lens Revox or the PestLeo or the LeoSams. And I want to do the I want to obtain the edge map using the low-cost LiDAR sensor. And so we want to use the solid-state LiDAR, such as the Revox HEP. And as you see here, it has very limited field of view in comparison with the Velodyne, the rotating type, the LiDAR sensor. And we have to compare the performances, including the 3D absolute trajectory error or the final drift error. And as you see here, the PestLeo shows best performance even in the long distance traveled situation. So the PestLeo shows the best performance, or the LeoSam or the PestLeo shows best performance on the final drift error. And one of the interesting about this result is that, as you see here, the Velodyne LiDAR sensor shows more sparse point cloud. However, the solid-state LiDAR, such as the HEP, shows more the dense point cloud. So as you see here, the performance about the final drift error using the Velodyne sensor has a lower performance than the HEP cases. So that's why we use the HEP cases for the solid-state LiDAR also. And also, one of the advantage of the solid-state LiDAR is that we can easily obtain the color mapping, because as you see in the previous slide, and the solid-state LiDAR has a very similar the field of view of the camera, so it's very easy to calibrate the camera and the LiDAR sensor. Then we can get easily the color point cloud map that you see in this result. However, unfortunately, there are many problems of the LiDAR SLAM because of the drifted area. For example, as you see in the bottom figure, there is a Rohan horizon also shows the drifted area when the largely traveled data set. And also Lens Revox or the PestLeo. As you see here, the PestLeo shows the best performance on the ATE or the final drift error, but it also shows has some drifted area issues. And this issue is very important to draw the edge map, because if we get the precise edge map, then the safety for the mobile robot is achieved. But unfortunately, if the drifted error is occurred in these cases, we cannot draw the precise edge map, which result in the unsafety of the outdoor mobile robots. So because of these issues, we use the LeoSam technology, because the LeoSam exploited the IMU and the loop closet techniques. So we use the LeoSam to generate the edge map here. So my next step for the hardware development is that we have to do the planning algorithm. However, as you know, the planning only on the sidewalk is not easy. For example, you have some point cloud map, and let's think about you have to plan the trajectory of the mobile robot. In that cases, you have to inspect the point cloud and you have to recognize where the sidewalk is. Then you have to generate we have the trajectory for the global path, and you have to do the local path on the sidewalk generation. That kind of things are very complicated. And also the integration of the planning and the localization or the perception is very difficult. So instead of developing each component, we want to use the AutoWare software platform, and the AutoWare is the integrated open source based autonomous driving software platform implemented on ROS. And it gives the integrated platform such as the entity matching for the localizations or the open source planner, so open source planner. So they generate the global paths, and they also give the control commands such as the pure pursuit algorithms and algorithms. So if you want to use the AutoWare software, you have to prepare the edge map. So that's why we use the generate the edge map here. So our main contribution on the mobile robot is that we designed the bidirectional road method for the automobile robot, and we also developed the Caldera simulator using our generated edge map or the point cloud situations. And to verify our algorithm, we prepared the 3 cases. The first case is about the load following, and the second part is about the sidewalk following uphill, and third scenario is about the sidewalk following on the downhill, and this is the result. And as you see, this is the Caldera simulation result. So in the first scenario, the vehicle can follow the specific road satisfactorily. And also in the second or the third scenario, so the bicycle seems very interesting. Anyway, they can follow the sidewalk satisfactorily. And this is the trajectory tracking error. As you see here, the blue line is the actual path, and the red line is the desired path. So by using the open source AutoWare platform, then we can achieve the very, very satisfactory tracking performances. And this is the auto scenario test. And first part is about the load following cases, and second and third part is about the trajectory sidewalk performances. One of the interesting is that by using the edge map signals, that we can set the stop lines before the crosswalk. So by using these skills, then the mobile robot will stop before the crosswalk. Then they can easily detect the vehicles or the humans while the crosswalk, so they can help increase the safety of the issues. However, unfortunately, there are many things to have to resolve. For example, as you see in the previous experimental video, there are some deviation from the sidewalk while driving, because the sidewalk area is, as I said before, is a significantly narrower environment than the road. So because of these issues, the localization error may occur on the sidewalk, because it is difficult to draw the precise edge map on the sidewalk from the point cloud map. And also, if the dynamic obstacles existed, then the AutoWare software platform does not guarantee the 100% dynamic obstacle avoidance performances. So you have to develop the dynamic obstacle algorithm your own. So that is a major issue about the AutoWare software platform. So our solution is that we have to keep doing research for this kind of method by using the HMAP or the computer vision technology. So maybe the HMAP with the computer vision or the learning technology will be the best solution for the sidewalk navigation. So this part is about the hardware platform developments. And so let's move on to the next part. So next part is about the navigation on the bad weather. So using the monocular depth estimation. And the details can be found on our paper, but unfortunately, the 2 papers are in the under revision. So any comment will be welcomed. So let's think about the monocular depth estimation. So the depth information is essential technology. So in order to move the UGVs or UAVs in the clutter environment, so the depth information can be obtained by the LiDAR or the RGBD or the stereo cameras. However, as you know, the LiDAR sensor, the cost for the LiDAR sensor is very high, and it is very heavy to equip the small size of drones or the mobile robots. And instead of LiDAR, some people use the RGBD camera or the stereo camera. But however, as you know, the RGBD camera suffers from the short range. It's maybe the 5 meters in the outdoors, or it's very weak to direct sunlight. So because of these issues, many researchers use the stereo camera instead to obtain the depth images. However, it also suffers from the low field of view. Maybe the 90-degree will be the best, maybe the largest field of view, I think. So that also caused a problem. So because the monocular camera is very cheap and very lightweight, so it has a very great possibility to obtain the depth images instead of using the stereo camera or the RGB camera. And monocular depth estimation is nothing but the technology that the depth estimation from 2D images, as shown in the bottom figure, then by using the deep learning network, then we can obtain or we can estimate the 3D depth images using the monocular camera. And the monocular depth estimation can be categorized into the 2 parts. For example, the supervised learning with the real world scale, or the unsupervised learning with the no real world skills. So in my cases, we want to develop the supervised learning technology. So let's think about the Waymo's vehicle. And as you see here, they also equip the 360 degree of the camera to detect the surrounding obstacles. So that's why the field of view of the stereo camera is unnecessary. So this is also the challenging problem for the stereo camera. So one of the major advantages of the monocular test estimation is that we can develop the dynamic obstacle avoidance algorithm for the micro size quadrature. So for example, the very micro size or small size of the drones can only equip the only monocular camera. And by exploiting the monocular test estimation skills, then we can do the more complex work, including the trajectory predictions or the path avoidance using the depth images. For example, let's think about the scenarios that the monocular camera generated the RGB images, and by using the monocular test estimation, we can get the depth images, and we can predict the obstacles. And the major technology to handle this issue is that some researchers use the Beans Mono or the Warabi SLAM to get the point cloud. However, in that cases, they cannot handle the dynamic obstacle cases because they use the picture-based technology. So if the dynamic obstacle are on my images, so we cannot track the dynamic obstacles correctly. But by using, however, as you see in the monocular test estimation, this is nothing but the end-to-end learning technologies, so they can easily predict the obstacle cases in the outdoor scenarios. So let's think about let's see some example scenarios. So as you see here, the very small size of the DJI Tello drone, and only equipped with the monocular camera. And by this is the left images is the estimated depth images. And by using the planning structure is that by using the simple planning structure, then the mobile robot can avoid the obstacles. The major strategy in this case is that drone should go the point where the depth is largest. Then they can avoid the obstacle satisfactorily. And this is a very simple result. And also this is the open source test. So in this case, we use the open source planning algorithm, which is the PEST planner, and the PEST planner is developed based on the Bernstein polynomial optimization process. And as you see here, this is the RGB images and depth images that we can generate the 3D point cloud map. And then by using this technology, also using the PEST planner technology, then the micro size quadrature can avoid the complicated obstacles. And also by using the technology of the monocular test estimation, as I said before, we can predict the trajectory of the dynamic obstacle, as you see here. Then this is the dynamic obstacle for the humans are here. Then the left images are the estimated depth, and this is the uncertainty of the humans, the network. So in this case, is by using the prediction of the trajectory, then the drone can intelligently decide where I should go. So the different direction of the people moving, right? And also this is the experimental result on the clutter environment. If, for example, the black dot is the tree, and the red line is the offline trajectory, which is obtained by the Bernstein polynomial optimization. And also by using the monocular depth estimations, so they decide the people goes here, so the drones move the different directions. So they will be the intelligent way to avoid the dynamic obstacles. So by using the monocular test estimation, that kind of things can be happen in very intelligent way. However, unfortunately, there are many challenges for the monocular test estimation. Is that the state-of-art monocular test estimation requires very heavy computation on the mobile platforms. For example, the high-precision monocular test estimation requires over 400 megahertz for the precise depth map, such as in GPU with the RTX 2080 Ti. But as you see here, that this cannot be done on the real time on the small size of mobile robot or the drone. So we cannot use this state-of-art algorithm. And also, as you see in the bottom figure, it suffers from the low accuracy for the unlearned or the unseen environments. So as you see here, this is the test result by the open source, and this is the kitty data, and this is the data that is data with the ground truth, and bottom side is a deep depth estimation. So we want to train our deep learning network using the Kitty dataset, and we want to validate our network to the Apollo, which is unseen environment. And as you see here, the Kitty trained and Kitty test shows 96% accuracy. However, as you see in the Apollo cases, which is the unseen environment, they only shows 4%. So that kind of things very great problem for the molecular test estimation. And also, molecular test estimation shows poor accuracy near the repeated simple or the monochromatic structures. So we have to resolve these issues. So how can we resolve these issues? We first propose the method to resolve the heavy computations. So we want to design the lightweight deep neural network by exploiting the encoder or decoder structures. So in the encoder structures, we want to use the Componex V2, and which is very lightweight, and this is developed by the Keist. And we also use the very complicated decoder structure by using the SSFF layer, and also use the PPM, the pyramid method, and to understand the global picture of the deep learning networks. And by designing by these simple structures, then we can our learning parameter shows 50 million in comparison with the state of algorithm. So UCRF or the GLP depths shows the 60 millions, or the 270 million is very large. So it's very slow to compute the it's slower to obtain the real-time depth images. So our case is more smaller size of the parameters. And also to handle the accuracy on the repeated simple structure or the unlearned environment, we designed also to enlarge the FOV of the stereo camera. So we designed the depth refinement algorithm with this wide stereo camera. And in these cases, we designed the fusion with the reliable stereo depth and the deep depth estimation, so we can enlarge the FOV. And so we also developed the dataset fusion algorithms. And this is the dataset validations. This is the Kitty dataset trained, and Kitty and the Apollo test result. And as you see here, in comparison with our state-of-art algorithm, our algorithm shows more the great performance in comparison with even in the unlearned environment, such as the Apollo cases. And this is the data validation. So our algorithm shows more close to the ground truth dataset. And also this is the Apollo test data, which is the unseen environment. And our algorithm shows more the close to the ground truth images. And you also test our algorithm in the outdoor scenario. And as you see here, to understand the performance of our algorithm, we prepare for the dataset collection with the camera with the LiDAR setup. And this is the test result. And as you see here, our algorithm shows very satisfactory test estimation result in comparison with the state-of-art algorithms. So my next goal is about that we have to develop the depth estimation with for handling the bad weather. So summer camera shows the clear images in the heavy weather because the summer camera exploited the LWIR waveband signals, so they can measure the heat even in the dark smoke. So we want to use the summer camera instead. So as you see here, the molecular depth estimation can be easily transformed to the summer depth images. And as you see here, so because they share the cost function for the network and the network structure are very similar, but you have to only to do is that you have to prepare the summer depth dataset generation. So as you see here in the clear RGB images, or this result trained by NYU, the indoor RGB images, and RGB depth data. And if we use the summer images input, in these cases, the test estimation will be bad, but by using our data set, so we can get the more clear images. And also for the dark environment, then the RGB images cannot estimate the depth, right? So however, by exploiting the summer depth images by using the summer dataset generations, then we can get more precise depth estimation results. So that is my work. So this is the summary of our work. Is that in today's talk, I mainly talk about the autonomous mobile robot technology for the including the sidewalk generation or the mobile robots. And the biggest challenge for the autonomous mobile robot is the sidewalk detection on the followings, or the perception in the heavy weathers, or the trajectory prediction for the obstacles. And this is end of my research. And thank you for listening.
Okay, we have time for one very quick question, and we'll move on to the next presentation in the interest of time. Yes, go for it.
version of the first part of the point. Scans versus the heat mass.
Oh, really? Yeah.
Mass. Do you think HT maps provide any other advantages beyond just not having like a semantic standard? You can have like a perfect semantic segmentation. Do you think HT maps without like have more to offer?
Your question is about the HMAP and the HMAP and the segmentation. So the segmentation is perfect and the HMAP is not required, right? So your question. Okay. In my opinion, as you know, the deep learning technology does not guarantee the 100%. So I think it is impossible to obtain the 100% accurate sidewalk navigation. So if the mobile robot invade the road if the mobile robot hit the humans, then the cost for developing the mobile robot will be high. So that's why we want 100% accuracy. So in that case, I think the HMM is a possible solution and a good solution. So even if the accuracy for the sidewalk detection is increased, then HMM may be the alternative solution or the very good way to use the HMM. Yeah, thank you for the nice question.
Cool. Okay, hi everyone. My name is Georgia, and I will talk to you about our research at the U Darmstadt on interactive robot perception and learning for mobile manipulation robots. To start with 1 second. Yeah, so if we look at humans and how we learn, we have this holistic action perception loop where we act in the environment in order to perceive, but also we perceive in order to act. And this is an internal loop with which we effectively basically develop our sensory motor coordination. Oops, 1 second here, this thing. Okay. We build a representation of the world and also the dynamics of the world, right? And eventually we interactively explore and play in an environment and we learn new skills. And what I believe we should try to do is follow the same paradigm also for robotics in order to enable, in particular, these complex systems like humanoid mobile manipulation systems to acquire skills through interaction. And I believe that this is the path towards embodied intelligence. And I am basically suggesting to everybody that, okay, we have achieved quite a lot in mobile navigation, but now we have to focus on mobile manipulation because we combine mobility and manipulability, so we can bring the two worlds together. These robots are equipped with multiple sensors, so we can really take advantage of this sensorial information to build good representations of the world. And finally, we can do a wide range of tasks because these robots have an increased workspace because effectively they could reach anything in at least, of course, up to a limit. Therefore, they make them also be a very good and emblematic example of what we would like to have as robotic assistants in home environments, in hospitals, and so on. So in my research, I believe that one of the ways to enable learning for mobile manipulation and for achieving goals like similar to the ones of like human interactive learning is by deploying structure. And we will see in 3 examples that I will explain to you later how we can introduce structure in the way that we learn and plan mobile manipulation actions in order to achieve coordination of the different embodiments of the robot. We can basically employ embodied information, for example, from the embodied cameras in order to build a good scene representation of the world where the robot can effectively interact with. And finally, how we can keep driving the exploration of the robot and try to balance getting new information while being task-oriented, as we will see in the end. So yeah, well, let's start with the first objective of how we can coordinate such humanoid-like robots with mobile bases, with 2 arms, and so on. So how can we do this? In a work that we presented last year, and we also received the Best Paper Award for mobile manipulation, we took the perspective of considering mobile manipulation systems as basically a multi-agent system in some sense. And in particular, in this case, we focused on the mobile base and the robotic arm as 2 decoupled systems, which we try to coordinate. And in this case, we introduce a hybrid action space that tries to select which embodiment has to be selected when. And when I talk about hybrid action space, I mean the optimal base pose in SC2, so the pose of the body of the robot, and whether we should activate the arm in order to execute some manipulation task. And how can we learn with this kind of hybrid action space? Because effectively, our deep reinforcement learning algorithms only operate on continuous action spaces. So we, first of all, create a hybrid policy that it is composed of a continuous part and a discrete part. And we effectively condition the discrete action policy to the continuous action because we need to know where the robot is placed with respect to some object in order to activate or not the arm in order to do a manipulation task, right? You have to understand the reach. And in order to train with our favorite deep reinforcement learning algorithm, we have to do also a reparametrization trick following the Gamble softmax reparametrization. So having established that, the question is, how do we train now the robot to understand its own reach, to understand when, if I am standing here, can I really extend my arm to grasp something in front of me and so on. So we introduce our reachability behavior prior in order to bootstrap the learning of this notion of reachability. And we took a step back and we go some years, 10 years ago, and look into the works so that we're effectively trying to coordinate similarly mobile manipulator robots by building the operational workspace. Here you can see an example of the operational workspace for the left arm, where effectively you just sample in a very fine discretized way 60 poses, and then you compute whether or not you can find a solution and what is the manipulability score of each, let's say, pose. And this is, of course, discretized. Now, what we would do 10 years ago, we would take the floating base paradigm, we will invert this mapping, and we will cut it on the level of the floor such that we get the inverse reachability map. Effectively here, the bluer spots on the ground gives us an intuition that if we place the robot there with respect to this goal pose that it is, the arrow that is a random 60 pose, you may find an IK solution for it. So it gives you basically a notion of where should I place myself in order to reach for something. And so we said, okay, this is actually something that you have to pre-compute, you have to have it stored, and then you have to search. And if your solution is not already there pre-computed, you have to do it over and over again. So we said, okay, why don't we get this information and use it as an offline data set to train a smooth Q reachability map. So we took this information and we trained a reachability map that additionally takes into account the actual success of reaching a random 60 target. And obviously, because now we have a neural network, we get a completely different representation of the environment. And this is exactly the same pose. And in the case of the RL training, we get almost 100% success rate of reaching the poses versus some 70-something% with the discretized approach. Now, this is only local information about what is the next step that I should do in order to reach for a goal. But mobile manipulation is, in general, inherently long horizon. You need to navigate into a room that has obstacles. You need to find the target, and then you need to place yourself in a way that you can grasp something or manipulate something. So in order to use this prior reachability map that we trained, we introduced a novel formulation for training reinforcement learning called boosted hybrid reinforcement learning. This approach relies on the concept of boosting, that effectively what we do, we learn residuals of the Q function. So instead of trying to learn a residual on the policy space, that is actually extremely difficult and actually not so intuitive in the end of the day because of conflicting information, we operate on the Q function level. So what do? You start with your base problem. In this particular case, it was this simple reachability area of the robot that I showed you before. And then you move to the next task that you want to learn, and you effectively learn only the residual of the Q function. And think of it only what is the missing structure that I need in order to learn to solve a problem that it is more difficult. And this can go on eventually, and you also decrease the complexity because you don't learn from scratch. You keep the knowledge already stored, and basically your Q function learns only what it is relevant and difficult to the new problem. And what is also very interesting, that you can also handle changing observation spaces. So initially there was, for example, no object, but now you can incorporate in the new residuals in the Q function information of the state space that can have been augmented. And also what we have found to help a lot to promote basically faster learning is to add forward KL objective that gives you basically a bonus in the training of your policy for remembering good actions from your past behavior. So we started with this simple reachability in the locality of the robot, basically what is the next step that I should take to reach a goal. Then we navigated in a larger area, we added obstacles, and then we went to grasping into different configurations. And also when, for example, we want to find the clearance in order to grasp an object aimed at other obstacles. And what is very interesting is that this approach only deals with the problem of what is the next sub-goal pose of my robot and whether I should activate my arm in order to plan for a manipulation task or any policy that I want to deploy. And we can effectively transfer this approach directly into the real world without needing any further training, because it's one level of abstraction higher than directly training on, on directly the coordination of the robot. And as you can see, we can also use the same strategy to do rearrangements, because if you learn how to reach in order to pick, you also know how to reach in order to place in a specific pose. And you can do this sequentially over and over again. And as you can see, the robot really finds poses that if you were really trying to navigate it like with a remote controller, believe me, it would have been extremely difficult also because this robot is differential drive. So yeah, this was a part of like how we can learn to coordinate, but how we could also have specific policies about different embodiments on the robot and try to coordinate them with one another in order to do whole body control effectively. In these high dimensional systems with the high degrees of freedom, actually having a valid whole body controller that can handle self-collision avoidance and collisions with the environment is a big problem. And we have to make also a lot of assumptions when we are actually optimizing over these different multimodal objectives. So if we take a look into how we can generate motion, I think we have like two approaches, right? We have these reactive motion controllers that basically rely on either operational space control or Riemannian motion policies, where they consider a different, basically, topological space around, for example, obstacles, which are very cheap computationally. They run on a high frequency, but they only do a one-step optimization. On the other hand, we have planning-based motion generation, like MPC style, which can do, look ahead trajectory optimization. However, they are typically quite slow and lower frequency. So we introduced in L4DC this year a method of using optimal transport in order to balance the different objectives as if they were different controllers that they need to coordinate in order to succeed into different objectives. In order to do this, we consider that the different controllers form a product of experts. And the weighting, the temperature basically of these experts is the parameter that we need to optimize in order to understand how to balance all these different controllers in order to achieve an overall goal. And in order to do this, while we have previously considered a probabilistic approach, in L4DC, we introduced an optimal transport approach. In this case, we consider that our controllers are agents, and we have a mixture of expert agents, and we try to balance their contribution to the final task, which, for example, in this simple scenario is to pass over this obstacle, while operational space controller or even Riemannian motion policies will get stuck into a local minima. So you try to unbalance and in some sense stretch the space differently in order to allow for finding a solution. So what do? We parallelize this rollout of the expert policies that each of them has a different basically objective, like obstacle avoidance, reaching, and so on. We compute the costs, for example, for reaching some goal, and then we optimize these blending weights of these different experts using an entropic regularized and balanced optimal transport. And we do this using discrete optimal transport and considering that these weights are some sort of histograms that we want to optimize. And we use this unbalanced version of optimal transport, but because it effectively allows us to turn off experts completely. And this gets optimized using Sighon-Knop algorithm using entropy regularization to allow us to operate on high dimensional spaces. And we are able to operate in milliseconds. And this gives you extreme speed on how to optimize different experts. And as you can see, we can have basically, in essence, reactive planning and control, even in very dynamic environments. We can also use it in some manipulation with some moving obstacles. It is deterministic, however, it is so fast that you can account for uncertainty. And effectively, we can also use it to coordinate robot in some very challenging whole body control tasks, even with moving obstacles and so on. And this is, I believe, a very promising approach. So we've seen how we can coordinate mobile manipulations, or like the directions that we propose for mobile manipulation coordination. And the next step is how we can represent the scene geometry so that the robot can interact with the world. One of the problems that we have that we didn't tackle in the previous work is how can the robot effectively see the scene from a partial view, from any viewpoint, and be able to infer grasps, which could be also task specific. So we are dealing with partial visual information. We want to use a single view. So in this case, we don't consider aggregating information. And we want to be able to do it from any random viewpoint, because effectively you have a mobile manipulator that can move the head, and it can also, for example, with the torso, go up and down, the base can move around. So yeah, you can have any random viewpoint compared to some static setups that we have in static manipulation, statically installed manipulation. And these are two examples of like views that the robot gets in some two different instances. Now, classical approaches fail a lot in these situations, especially because you have very weird viewpoints from the robot. So we took a different perspective and we thought of reimagining grasping as rendering. So taking advantage of what is happening now in neural surface rendering, we propose a new pipeline to completely use and exploit neural geometry in order to learn fully implicit 6D grasp detectors. So how does this work? So we, first of all, create a representation of the scene. We use a classical convolutional occupancy network, and we do we train for scene reconstruction. And then what we can do scene completion from any partial view, and we can query at any resolution. And now the question is, okay, you have the scene, you completed it, how you can extract good features for grasping. So as I said, we reimagine grasping as rendering. And first of all, what we do in this now completed scene, we generate grasp candidates even in areas that have not been really perceived, right? So here on the left, you can see a point cloud view. We do neural rendering, so we do ray matching, and we exploit the occupancy network that we are training in order to complete areas of the scene that have not been seen by the robot. And then on this new completed scene, then we query for possible grasps. And now we have to evaluate these grasps. So as I said, we have unseen grasp. We can be arbitrarily dense because we can even change the how fine-grained the point cloud that we are rendering is. So this gives us also additional information, and we could include also additional constraints about like reachability, semantics, if you want to include some affordance and on how you are going to sample. But then effectively sample is like halfway through, then you need to evaluate how good are my grasp samples. So in order to do this, we do a fully implicit quality prediction network that also renders the local information that the gripper sees on the surface of the object. So what we try to do, we place virtual cameras on the gripper, and we see how does the surface look like from the point of view of the gripper. And this effectively, we train also for occupancy also there and the reconstruction, which means that we extract local features and also in a very fine grain scale. So we really can capture very rich representations about how the gripper effectively interact with the surface of the object. And yeah, so we get this, let's say, feature extraction that completely represent the full 6D representation, because till now, state-of-the-art methods, what they do is that they separate most of the times. They are implicit in position, but they regress for orientation. And regressing in SO3 is very, very difficult. Therefore, in this case, we alleviate this need for having any sort of regression in orientation. And additionally, this comes with the benefit of better reconstruction, because you get more fine-grained information on the surface of objects. So the pipeline, you place the robot in some pre-grasp pose that renders, basically takes a point cloud view of the scene. We render the scene and we complete it. We do grasp sampling and then we do grasp detection. So we only allow for the good grasps to remain, and then we do grasp execution, in this case with a classical planner. So if we see a bit the evaluation, you can see how nicely we render the scene. With green, with red is the reconstruction. With yellow, you can see the proposal grasps, and with green, the good grasps that we detect. And if we see also comparatively to the state-of-the-art methods that are mainly implicit, so they also do grasp detection, you can see the benefits in grasp success and also decluttering. So how many objects you are able to successfully remove from the scene without collisions, like and people flying away and so on. And we can effectively, again, transfer this in the real world without much loss in performance. And as you can see here, we fixed the position of the robot. We do the decluttering. However, as we said, we are dealing with mobile manipulation systems, so we can also move the robot around, change the viewpoint, and being able effectively to also select from which side we want to complete the scene and grasp objects and continue with the decluttering. So yes, and finally, yeah, as we said, humans always try to explore. We always try to minimize some sort of uncertainty that we have about the world, or we try to gain more and more information or else knowledge, but still we need to learn some sort of task. So in our latest work, we try to see how we can make mobile manipulators being able to perceive and act. So basically these two things to come together in unstructured, cluttered environments using their embodied camera. So again, we have the restriction that we can only use the camera that is mounted on the robot, and we need to actively perceive and explore in order to obtain this task-relevant information, which again, in our case, it's grasping. So the question is how, when do we have sufficient information in order to execute a task and ensure that the robot can really execute it? So if we look into active perception, most works are dealing with scene reconstruction. However, and for grasping, even unlike static manipulation, the range of motions that the mobile manipulator has to do are expensive, and wasteful motions just to reconstruct the whole scene and then query, for example, grasps and so on, is quite wasteful. Therefore, we need some sort of time and energy efficient solutions for mobile manipulation robots. So our problem setting, as I said, is a bimanual mobile manipulator robot with an embodied camera, and we make the assumption that we somehow are in a scene that we have never seen before, but we somehow know some approximate bounding box that you can see here of some object that we need to grasp, which could have come, for example, from a user instruction that would be like pick up the object at the right corner of the table. So during an episode, the robot builds a volumetric representation of the scene, effectively a TSDF, and then uses this for active perception and grasp detection. So what we propose is motion generation for through active perception for mobile manipulation, where at each time step, we sample candidate paths for the robot, which in this case is effectively base and camera poses towards some goal locations that are roughly approximately sampled to be in the reachability space of this approximate target area that we want to reach in order to find the object that we need to grasp. And we formulate this problem as a resetting horizon control, where we try to find the best path that balances the information gain that you gain from doing the scene reconstruction, while trying to balance for the execution, which has to do with executability of the grasp, whether the grasp that you detect is reachable by the robot and whether you should execute it or not, based also on some threshold of grasp quality that you detect with a grasp detector. And here you can see that we effectively, what we propose compared to next best view approaches is actually a pathwise aggregation of the expected gain that you are going to have in information and executability by aggregating the information gain that is effectively the information gain that you expect to find by placing the robot in a specific pose, which is penalized by the distance that you will have to move to, because as we said, we want to be efficient for mobile manipulation. And for the executability, we are looking into what is the reachability of going in a pose and effectively being in that pose, being able to directly grasp an object and not having to move in another configuration to find a solution. Again, divided by the length that you need to move to. And we found that these distance metrics are important for balancing better the exploration of the robot. So, and we also do this at every step. So we recompute, we go to a next best, let's say, view, a next best pose of the robot, and then we recompute this objective to ensure reactivity to new information, new grasps that you may have perceived, collision checks, because there's also collisions in the world that you move around, you detect, for example, obstacles and so on. So what we do, we spawn the robot in the environment, and we start sampling trajectories towards these goal bases till the robot finds a grasp that it is highly executable and therefore stops the reconstruction of the scene, and it's basically completely task-oriented. So this is basically the difference between trying to reconstruct the whole scene versus, okay, I need to do this task, I would do it as fast as possible. So if you want to take a look a bit more into the utilities here, you can see how the information gain is being completed from a new viewpoint with the blue points there of the scene. And this is basically the reachability map of the robot for both arms. So in this case, we are balancing both objectives. This is actually the workspace. As I said in the previous work, we are considering it on the floor for placing the base. We did a thorough hyperparameter search, and we all found out we were wondering if it really you need this executability score, given that you are sampling goal bases that are already supposed to be reachable, and you are actually updating these goal bases at every step. And it seems that if you consider hard grasp, so one thing that I haven't said here, as grasp detector, here we have used the VGN network, that it is trained in such a way that it favors top-down grasps, and these were very easy to execute, especially in this setup that we have, like with the small table and all the objects like this. But if you only restrict it to have hard grasps, meaning side grasps, so not top-down grasps, you see that balancing the reachability together with the information gain is essential, especially if you have scenes that have more occlusions. And we are currently working on more difficult setups to see the benefits. So yeah, finally, we can see also how differs the next best view approach that doesn't take this pathwise aggregation compared to only selecting the next best view based on the instant information and not the expected information and executability. And yeah, here you can see the real world execution of the robot that starts on the other side of the room and knows more or less where it has to go. It perceives the scene, it finds the object, and places itself in a grasp position to execute the grasp. So as a takeaway message, so we need this coordination. So it's not always easy to solve a whole body planning and control problem at once. So maybe consider the coordination of the different embodiments for mobile manipulation is an effective way to go. Neural geometric representations are necessary for skill learning, for building a good geometric understanding. And finally, there is a crucial interplay of perception and action, and we need to find the right trade-off, basically among these two, especially if we are dealing with mobile manipulation. So yeah, I would like to thank you, and I'm open for your questions.
Great, we have time for questions.
Question about this kind of the visual representation. But how can you get over failures from the shape?
So what we have seen is that first of all, we have a data set of like million scenes, over a million scenes. So it has a very broad combination of objects. What we have seen is that in general, the network captured some basic shape. So even if you bring it in some object that it has not seen in training, it is still able to do some sort of completion of it. And in most cases, this is enough for doing the grasping. So completing the surface. It's not completely solved, but it is very close to be solved given enough data, I would imagine. Then what I would say that it is the next step is to actively updating your representation given new data. So it's about active learning after this point. Yeah, actively perceive to then update the representation, because I would say that the active perception is like the exploration phase that we can then leverage for doing learning. Yeah, this is related to not the hybrid action space, but I mean, it's still hybrid. It's more related to the whole body control that I presented with the different controllers. So one of the problems of operational space control, first of all, is that it doesn't scale well for problems that where you have to do SE3 manipulations, because you basically have distances in Euclidean space. And when you are considering Riemannian policies, then it's very, very okay, you have a different representation of the world, but still it falls into many local minima. It needs a lot of engineering effort. So being able to learn how to coordinate which to use when, it's the best. And also if you have done ever operational based whole body control, basically QP control with a mobile robot, because most of the times it is easier, and how the task priorities are very tricky to tune, right? What happens is that you have a zombie robot in your home. So your goal is to reach and open for something. Therefore, you have a zombie robot moving towards a handle. And then because the easier solution to most objective is to stay like this, you will see a robot that doesn't have this more natural, for example, solution that a human would do, right? So yeah, I think that learning can replace wherever engineering effort is needed right now.
Great. Let's thank Georgia for this exciting.
All right. So thank you very much for the award, and thank you very much to the organizers for putting this together and giving me the opportunity to speak here. It's great to be back here at IROS. I apologize in advance if my voice seems hoarse at times. I haven't slept for 36 hours straight, and I've been talking since morning. So let's get into it. My name is Rohan, and my research is focusing on human-like mobility to deploy robots everywhere. What this means is that I focus on algorithms and systems that enable robots to navigate among humans like humans. And just to set the agenda for today, I'm going to start by giving an introduction to my research, what I do, why I do it, some of the challenges that I like to solve that keep me up at night. I'm going to summarize my research vision. More specifically, I'm going to talk about very briefly. I'm going to summarize how I work on perception, reasoning, and planning that enables and develops a human-like mobility for challenging human shared spaces. Now, I did sort of like debate whether to do like a 30-30-30 split into each of these areas, or deep dive into one of them, and decided to go with a deep dive. So I'm going to just sort of gloss over the perception and reasoning stuff, and I'm going to do a deep dive into planning. And I'm going to discuss some applications, some results, and I'll also talk about some new tools and simulators that we're developing at University of Texas, and how that can be used to develop new algorithms, new systems for human-like mobility, to enable robots to do more socially compliant navigation in challenging human shared environments. So with that, we can begin. So some of the grand challenge applications that I'm excited about solving include autonomous driving, last mile delivery, service robots, and personal home robots. And while these areas have seen tremendous progress in recent years in terms of the kind of multi-area navigation that goes into it, we're still not at a point where we can confidently and safely integrate these robots into the fabric of human life. And what do I mean by that? What I mean is that even though robots can do autonomous navigation fairly well, according to some definition of well, they cannot still do tasks like they cannot shop for our groceries, they cannot pick up our medicines, they cannot run through a crowded airport to catch a flight that they might be late for. They cannot drive through general traffic, right? You have Cruise, you have the Tesla, Waymo, you have all of those vehicles, but they require a lot of geofencing. They require mapping, localization, and they require so many miles of simulation and experience. If you plonk a general autonomous vehicle in any kind of traffic, it won't work well. If you try to take it out of the US into developing nations like India, it won't work well. So these are some kind of challenging environments that I'm very excited about solving. And when you think about these applications, the next question is, what kind of challenges that do you have to contend with? Before we get into that, I want to show you a real world example of how these sort of like autonomous robots might not work very well in the real world. So this is an example. This is a video of the Cruise autonomous vehicle. Cruise is one of the state-of-the-art autonomous vehicle, autonomous driving technology out there. And this video is not even that old. This is a very recent, very new video taken in UT Austin campus. And so it's not like the technology is also very, very old. Technology is latest on the Cruise vehicle. So as you can see, there's a traffic jam that has been set up by the Cruise vehicles, and it's caused by these two vehicles over here. And what's happening over here? You can't make out too well, but what's sort of happening is that these two vehicles are in a deadlock, right? They're both trying to turn right. So the vehicle in front is trying to turn left, and the vehicle towards you is trying to turn right, and they're both in a deadlock. They're both frozen. Now, all of you have probably heard of the freezing robot problem, right? And Robotics 101 class, you'll hear about freezing robot problem. This is freezing robot problem on a $1 billion scale. We don't have to go that far. We can conduct experiments on a laboratory scale, and we can see that even on simpler robots, we can sort of see that same sort of phenomena, where if you replicate in an intersection scenario, then this is a baseline navigation algorithm, and unless the human robot gives way to the robot does not move, and the human has to back up in order to let the robot move. So this is also another example of some of the challenges that plague robots in shared human environments. So some of the challenges that we might have to contend with are that the scene might be too complex, right? So the scene complexity includes complexity from geometric sources, right? Like the size of the environment might be too small. There might be too many physical obstacles. There might be very narrow spaces that the robot has to go through. The complexity can be in terms of the semantic elements, which includes includes objects that the robot has to recognize, right? In order to navigate well, it needs to probably know that this is a table, this is a chair, and a table is probably larger than a chair, right? So it has to know the semantics of the environment, and it has to understand the dynamical entities. It needs to be able to reason about and understand the dynamical entities. So what that means is it needs to be able to track moving pedestrians, moving animals, moving stuff. It needs to be able to detect them, localize them, even forecast their motion, and so on. So the more agents you put in a scene, the harder it gets. The more different kinds of agents you put in a scene, you put a two-wheeler, three-wheeler, pedestrian, even animals on the road in the case of India. So all of these things like contributes to the heterogeneity and contributes to the complexity of the scene. The more unpredictability on the part of the dynamic entities. For example, in the US, we have right-of-way rules. We expect people to behave in a certain way, but all those rules go out the window in certain cases where you may not expect the other people to follow the same rules. So all of this comes under complexity of the scene. Then you have the uncertainty. When you're dealing with shared human spaces and you're dealing with human agents, you may not know the objectives and the cost functions of the humans. So, and this is quite important because if you're trying to coexist in human shared spaces, then you need to be able to reason about their behavior, especially if you're interacting with them in tightly coupled scenarios. And the final thing is the multi-agent interaction, which basically tries to it asks how should we model these interactions, right? So should we model it as a joint prediction planning problem? Should we model it as a dynamic game? Should we model these agents as dynamic obstacles and just do collision avoidance? So how we model these multi-agent interactions is also a very important question. So that brings me to my research question, which is how can we make robots navigate safe, deadlock-free, and fully decentralized in a socially compliant way in shared human spaces? So, like I said before, my research focuses on human-like mobility framework. What this means is that I focus on these algorithm systems that try to tie in the various sources of complexity, that try to address these sources of complexity and do research along these three dimensions. So some of my previous and ongoing research in this area is along the lines of understanding these environments, which is a lot of perception stuff. So I've done object detection and tracking. I've done semantic segmentation for adverse environments like bad weather, bad time of the day, snowing, and all of that. I've done motion forecasting stuff. So motion forecasting, how do you predict the trajectory of the ego vehicle and the vehicles around it, and action recognition. So if your ego vehicle is driving, like can you predict or can you recognize just from RGB input, RGB video, RGB in, action out? So can you predict the action of the ego vehicle just from the RGB input? And all of these things are done on dense, heterogeneous, and unstructured environments. I also worked on modeling human behavior, which is defined as given the state of the environment, can you build a preference model? Can you estimate the preferences and the risks of the drivers around the ego vehicle, right? So I've worked on online, robust, and general risk estimation, which involves developing algorithms for a plug-and-play behavior estimation, preference estimation algorithm, which we were able to deploy in 4 different countries: US, China, India, and Singapore. And we were able to show that we can deploy this algorithm like in a plug-and-play format without any pre-processing or without any learning. So it's not a learning algorithm. Like it's complementary to techniques like inverse reinforcement learning. And finally, on the planning side, I've worked on behavior-aware navigation. So this is like a direct follow-up to the human behavior modeling, which is that if you can estimate the preferences and behaviors of the humans, how can you use that in downstream navigation? And some of my ongoing work is on how can you ensure liveness and collision-free guarantees for social navigation in shared human environments. So with that background out of the way, let me take a deep dive into my work on safe, deadlock-free, and fully decentralized navigation in tightly coupled human-robot interactions. So I'm going to model the environment as a partially observable stochastic game, right? And this is a fairly standard formulation where we have K agents who are trying to get from point A to point B, from the start position to the end position over a time horizon T. X is the state space. It's a finite continuous state space. Each agent has its own action space UI. Each agent also has a set of preferred trajectories gamma I tilde. So this is a set of preferred trajectories that each agent has a priori, right? So if I wanted to go from here to the end of the hallway, and if I'm an assertive person, I want to take a straight line path. Or if there are people in my way, and if I'm a conservative person, then I would probably take like a more circuitous path. So that would be my preferred trajectory. We have a transition function that takes in the joint state and the action of each agent. We have the observation function, and then we have the cost function that operates on the joint state and the action of the robot. Given this formulation of a partially observable stochastic game, we can define what we have termed as a social minigame. Social minigame, it has a formal definition, but just for the purpose of this talk, I'll keep it at a high level. So what this means is that during the course of the navigation of two agents, there exists a time duration during which all of the preferred trajectories for one agent will be in conflict with all of the preferred trajectories of the second agent, right? And we say that if that happens, if all of these preferred trajectories are in conflict, then we encounter a social minigame, right? And if there's a social minigame, then there will be a deadlock, and I'll show you why. So in order to solve this partially observable stochastic game, we frame this optimal control optimization. Of course, this should also not be something too alien. So we seek a policy pi I star, which attempts to minimize the error between the planned trajectory for agent I, xit, and the preferred trajectory xit tilde. So it tries to minimize this error over the time horizon t while satisfying several constraints, such as safety and collision avoidance constraints, the dynamics constraints, and the 2-point boundary value problem constraints. And so this is the formal definition for the social minigame. But what this essentially says, if you can want to parse this out, is that there exists two timestamps A and B during which all of the trajectories gamma I tilde and gamma j tilde will be in conflict. And what that means is that inside this sum that goes from t is equals to 0 to t minus 1, there will be certain xit tildes that will be in conflict for I and j, right? And when this happens, then there is not this optimization problem does not return a solution, and that is the mathematical sort of like the mathematical intuition behind which we enter a deadlock or a frozen robot problem. So our key idea is to use a bi-level optimization strategy where we apply a strategy F on the state space of the robot I that attempts to do some sort of conflict resolution on the preferred trajectories. So the bi-level optimization strategy consists of two levels. The top level does this conflict resolution, and it gives an output for this conflict resolution. It solves the conflict resolution problem, and the solution for this conflict resolution will be taken as a constraint for the bottom level optimization, which does the motion planning, right? So the optimal control problem remains the same, except that we introduce this bi-level optimization where we have this F as the top level, and we have the motion planning as the bottom level, and that could be, dynamic window approach or MPC or anything like that. So we started with using auctions as the top level protocol, right? What the auction does is it collects bits from all of these agents, from all of the robots, and an auction program, a central auction program, is going to compute a priority order over which it needs to resolve the conflict. So imagine you have an agents going through a doorway scenario, and the conflict is over, which agent will go first. And remember, all of these agents are trying to act autonomously, right? So each agent wants to go first, but which agent should go first is decided by the auction. How the auction mechanism works, I've linked a paper below, we can read that. But what it effectively does, we design a kind of auction which incentivizes robots or human drivers or human agents to participate in this auction, and they will receive a priority order which will tell which agent should go first through the door. This priority order is the solution for this top level optimization, which then feeds into the bottom level motion planning algorithm. The motion planning algorithm, it will still consider the same constraints, the collision avoidance constraints, the feasibility constraints, but it will now additionally also incorporate this priority order constraint as a top level solution. And we applied this in various applications, and what we found is that we started with a simple discrete domain application for multi-agent pathfinding. And we found that for strategic agents, for example, if you wanted to do multi-agent pathfinding for agents who have these private incentives, for example, one agent could be like, I want to go to the grocery store. Another agent could be, I want to go to the hospital. So they have these different incentives, and that causes a problem, and that makes it hard for conventional MAPF algorithms to solve. One is because the multi-agent pathfinding algorithms, conventional ones, use centralized algorithms, and two, they do not take private incentives into account. So what we extended the classical MAPF formulation to the social MAPF formulation, which takes these incentives into account, and we applied our bi-level optimization algorithm, and we found that we could in the discrete domain we could prove and give safety and liveness guarantees, but at the cost of losing at the cost of not having it fully decentralized. Because if we have this auction program, right? If we have this auction program, then by design we have a centralized auction server that's distributing all of these priority orders. So it's not fully decentralized in the case of in the case of a discrete application. We moved on to a continuous domain application. So we looked at autonomous intersection management. And I'm not sure if this is fully visible, but what I'm showing is two visuals of an autonomous intersection. On the left, this intersection is being controlled by traffic lights, and the input flow is identical, same across both scenarios. And on the right, I'm showing the application of our bi-level optimization approach. It's the same volume of vehicles, but you can see that the traffic light is a lot less efficient than the bi-level optimization. So this was another application for autonomous intersection management, but the only problem is that even though we could still guarantee safety and liveness, but we cannot do that in a fully decentralized way or even in a distributed manner, because we cannot leave the optimization and the controls to each individual vehicle. This is because the top level optimization, the auction optimization, is a discrete solver, whereas the bottom level motion planning is continuous. So we cannot transfer the guarantees to across both the levels. So that's the limitation of auctions as a top level. We cannot give guarantees on safety and liveness and continuous space, and it's not fully decentralized. So our second key idea was to change the top level to a perturbation instead, which now says that you instead of applying an auction, you perturb the state space of the agent such that it perturbs the states onto safe and deadlock-free regions. What these regions are, it's in the. I'll leave that as a separate thing. We can discuss it offline. But it perturbs the states onto safe and deadlock-free regions, and let's assume that they exist. Then we can use control barrier functions or CBFs to lock in the guarantees for safety and liveness via forward invariance. And we use the bottom level as before. So then Now that we have replaced the top level from a discrete optimization to a continuous optimization using projection onto these states, we can now guarantee the liveness and deadlock free. So now we compare with other deadlock resolution methods, and we show that in these three settings, doorway, intersection, hallway, we compare how smooth and efficient the perturbation actually is. So we compare average delta velocity and we compare path deviation. And the lower these values are, the smaller, the fewer changes in average velocity that you have, and the lesser that you deviate from the path, from the reference of the preferred path, the more better your perturbation is. And our game theoretic control barrier function approach achieves the smoothest perturbation and the smoothest deadlock-free resolution protocol among these deadlock resolution methods. We also compare with other navigation baselines. These are navigation methods that may or may not necessarily have a deadlock resolution component, which is why you see that in the first column, in both rows in the first column, our approach is able to handle these constrained environments, whereas all the other methods are sort of like entering into the deadlock. So I'm probably out of time. So I'm going to basically just quickly go through these results where I'm showing various robot morphologies, various kinds of robots, and I'm comparing bi-level optimization with a baseline dynamic window approach. So this is the case of 3 F110 car platforms going through a narrow doorway. Here I have a similar scenario with 2 F1 cars. This is a experiment with a Toyota and a Jackal and versus a Toyota and the HSR. Here's an intersection scenario. Here's another intersection scenario, which is including the F110 cars. And then here is a physical experiment with a human robot experiment. So since I'm almost out of time, let me just show you one scenario out of this full video, but I link the paper at the end and you can look at the full video offline. So here what I'm showing is a baseline algorithm is failing to yield to the human, right? Whereas the game theoretic approach successfully yields to the human as it should. In the second scenario, when the human deliberately slows down, the expected behavior is for the robot to speed up. So here, the human slows down and the robot also enters into a deadlock, which is from the same video I showed you in the beginning. But now, the game theoretic approach is going to recognize the human slowing down, and it's going to immediately speed up and avoid wasting time. Okay, so we extended the bi-level optimization. So I introduced a classical variation of it. We also extended this to into the multi-agent learning framework. And very quickly, I want to just, do I have time to? No more. No more time? All right. The next session. Okay, cool. So we just basically developed a simulator for multi-agent navigation, and it supports multi-agent RL. It supports all these social mini games. And I would really encourage you to check this out if you're interested in multi-agent navigation, both in the classical sense and in the from the learning sense. Okay, so for future work, basically, I want to work on everything perception. This is basically a foundational multimodal form of perception for human-like mobility, which combines different kinds of competencies. It combines tracking, segmentation into a single model that resembles the kind of perception that humans are very adept at in these environments. Second, I want to capture non-verbal cues. There are certain cues that humans give out, like gestures, body language, gaze, that can be formulated in the form of a language. And I want to see if we can then model these cues as via LLMs and then use that for reasoning guided or non-verbal cue guided navigation. And finally, in addition to safety and liveness, I'm also very excited about trying to see if we can introduce agility into these robots. So let's skip the summary. I want to thank my mentors and collaborators for their time and for all that I've learned from them. And thanks. I can take questions now. Okay, we are a bit behind time, so I would propose that we take questions for Rohan as part of the panel session, which he will be a participant in. So this is the last thing for today. Thank you for those of you who are still around. We're going to have a panel.
So in the end of the day, you need to be able to actively learn and explore, and as Kostas said, extract specific information, specific cues that may be also multisensorial, right? It cannot be just vision. Like many people are focusing on your vision, but in the end of the day, it's multiple cues that we have to take into account to build good representation on top of which we can act and learn and so on. So the representation, I think, is a big issue to consider.
Cool, thank you. Something? You can share the microphone. That's the idea, yeah.
Okay,
we let you speak.
I completely agree with Kostas and Giorgio. I think the example they gave from the screwdriver was from the manipulation point of view, and I can agree with that from the navigation point of view. That when I was studying robotics, I was studying the classical robotics 1.1 stack, which is perception, planning, control, right? But now more and more we're shifting towards the new stack, a new kind of stack, which is perception, reasoning, planning, and then control. And this reasoning is coming in the middle, even for navigation. Because when you perceive, when you look at, you do the object detection, and you track all the object, track all the agents, we need to have this middle step of reasoning about the other agents' intentions. And there's a whole field of human-robot interaction and in most learning, we're trying to estimate either the cost functions, the objective functions, or the preferences of the other agents. You're either employing imitation learning. There are various learning-based methods, learning from demonstration, and all of those things. But somewhere along the line, I think this all falls under a reasoning paradigm where we have to, given all of these visual features, visual information that we're gathering from the sensors, what do we do with them, and how can we extract the cues to enable and power downstream application? And I think I'm pretty much stepping on your points. So, yeah.
Thank you.
Yeah, okay. So going back to the meditation problem, I'm working on meditation and perception. I think one of the really big challenges in kind of integrating both perception and meditation, or kind of in general planning and control. I think one of the big challenges actually, as you may agree, the uncertainty in perception, because the perception usually may be in simulation, we assume the perfect knowledge about the state, but in reality, almost even the state of advanced always there is some uncertainty, right? And actually kind of make the uncertainty in the kind of control. So that's why I actually kind of thought about how to combine the perception and the kind of the control in a meaningful way. So yeah, it has been studied for a long time, but still kind of it feels like still we need to go further. That's kind of my
cool. Yeah, thank you. I will just pick on that screwdriver example because that was really interesting. However, I would like to understand the reason behind your reasoning of why this is interesting for robotics. Like, I understand for humans, but actually I don't know why humans would have this behavior, but why do you think that kind of thought process will be interesting for a robotics application?
Yeah, I can elaborate more on that, because I find it when I studied this domain, and I'm not doing manipulation at all, but it's studied a lot with respect to human action within workspaces. To study the human visual attention mechanism. And there are two aspects of it that are very relevant to robotics. One is compression. The whole idea is that you are looking to few things, so it's a means of compression, and so attention means compression, which means then prioritize action. So that's the first very important thing. And goes to navigation also, right? So the fact that, for example, we are not now anymore living in a jungle or anything like this, but the fact that if something, comes out on the left of your eye, you're going to act immediately. That's because there is intentional attention, which then means compression, which then means low latency, which then means fast action.
I see.
So there's a very nice field of work that it's not to be mimicked. I actually disagree a little with biomimicking for robotics, but to give inspiration. And I think what we are missing a lot is two things on the basis of this paradigm. Knowing where to attend for the task, number one, so that's top down. And then we're also missing bottom up, knowing what to attend in general to reduce uncertainty for future tasks that we currently are not in the pipeline to execute. Right? So for example, that's also for the case for a driver. You see a kid maybe playing with a ball on the left side. That's a typical example when we did driver school. You see a kid with a ball, prepare that the kid might just jump on the road. Right? And of course, there is no robot currently that does any reason of that level, unless the kid's actually on a trajectory to enter the road, and maybe this flags a camera filter or something to account for it. There is no action space at the moment to say that, yeah, I should attend to this so that potentially might enter in my direction of drive. So there are two aspects. There's top-down aspect and there's a bottom-up aspect of perception to action.
Cool, thank you. Do you have any questions or anything to be raised by anyone in the audience? Please can you send the microphone?
Thanks a lot for the session. So I have just a stage question or weird question. So can we have a robot of agnostic stack? Let's say we have this perception planning and control software. Can I, in future or presently, can I have such a software that can be deployed on any robot, even a self-driving car or a robot family? Like, is there any idea or some more research on this?
Navigation, I don't know. For navigation, no. For manipulation, they currently do some efforts, but I don't think they are so structured in the way that you describe, because of things left out to language models doing the reasoning and so on. So yes, as far as I know, there are like large efforts to collect very big data sets to train like robotic models. For manipulation, for example, how well this will be transferable. It also depends on what is the space on which you represent actions, for example, with respect to the perceptive signals. The question is, are they object-centric? So there was a lot of effort quite some time now in learning-based representations where we're saying, okay, everything has to be object-centric. But then on the other hand, every robot has its own abilities. Like it can be that the same robot from the same brand has slightly different dynamics, or maybe the kinematic chain is not exactly the same, or the gripper is slightly different. Shouldn't this be in general optimized in any case to the skills? Like I don't think there is a human and another human doing the thing exactly the same way in a very general environment, right? We're not talking about automation when there is no uncertainty, there is no things considered.
Yes, I think the better way to formulate the same question is such a foundational work. Can we identify something that is largely common as a first layer of training that afterwards we specialize with subsequent layers? So I think that's a more interesting way to express the question. Also, for example, vastly different tasks such as navigation and manipulation. We shouldn't expect that they are actually on the exactly this base software, let's say. But the key question is, if we develop this foundation, large data set foundational models, can they represent a core around which more modules are trained further or developed further? But that would be my approach at least.
This has been kind of introduced with from Facebook, the visual cortex.
Yeah.
But it's not that good for manipulation in the end. So I think that we are still very far away to exactly. I think the point is what you were saying also before. What are the informative cues? What carries information gain? What is relevant to the action that you do, and which action then is going to also augment your understanding about the world? So I think it's this. The stack should be more. A more interactive circle than the plain, even if it has the reasoning, in between, because even if it has like perception, reasoning, planning, action, you need to loop around the different components, and I don't think they should be disconnected from each other. So as long as we don't have this very nice interconnection in a way that we suppose also the human brain works, I don't think we are going to solve it and be able to generalize, because what we would mean by this, it would be generalization of the human that drives the car and the human that can, I don't know, take the screwdriver and like screw a... Yeah, exactly.
Yeah, and as far as I know, like the way people are approaching navigation in terms of the kind of like people are now thinking about building foundational cores for like navigation that can support that can act as a core. I think the way people are still thinking about it as of today is still like you have a classical stack that works fairly well, right? And they're picking up blocks of that stack and then replacing it by learning one by one, right? So there is like a very nice, even survey paper that talks that actually does this study in very detailed, that, you have a few end-to-end learning models, but they don't work very well. But then on the other hand, you have classical methods with tons of experience and tons of, evidence and some guarantees and properties. And now what you're doing is you're picking each part of the stack, each block, replacing it with the learning module, seeing what changes, what breaks, it's working well, and you're building on top of it. Right, replacing each block, it works well, okay, you move on. But as far as I know, I don't think there's any end-to-end learning method in deployment, at least, especially not for RL. Like if you use learning for control, I haven't seen any commercial deployment so far. There has been tons of commercial deployment for learning for the perception block. Little bit on the reasoning, like I interned at NVIDIA and working on the project which did we're still like using learning for the reasoning prediction part of the driver. So it's still very naive technology like that. So I think this the philosophy is still pick up blocks of the stack, tack on learning, see what happens, see what falls, see what breaks, and then go on from there. But we're still nowhere near developing a commercial deployment of an end-to-end learning or a foundation model.
Yeah, I think I agree with you. So in general, it's really hard to have one really good model that can be applied to different kind of robotic system, because robotics in general is actually embodied system. So you may have a different kind of sensor. So maybe the way that it kind of process the data and also make this decision might be quite different depending on the kind of application and so the kind of the task that robots need to solve. So maybe, well, I think the closest thing maybe we can think of is maybe using some kind of a generic AI, like a large language model, as a kind of the high-level reasoning model. So maybe they can, because it's kind of our human knowledge is somewhat encoded in that kind of model. So maybe we can use some kind of the semantic understanding and reasoning. So, but still we need to kind of fill the gap between the kind of high level understanding planning to the low level control. So maybe there are some kind of several layers that we need to take care of it. But I think it's very hard to do.
Yeah, I can say one more thing. Just to add, because I think it's a very relevant question in many ways, I want to challenge the following thought. I'm working on flying systems, but I'll say some of many systems. Quadrotor, which we think that is relatively new, was designed in 1908, which is essentially the beginning of the 20th century. Helicopters, airplanes, all overseeing drones, for example, miniaturizations on off-man designs. Vehicles that we're trying to automate are man designs. Manipulators that people are working pretty much are, things that were, or for example, we're working on humanoids now and it's replication of human concept, right? I think the more interesting question is the following, which will be an extension of what you're saying. If there is something foundational across different tasks, then the interesting question is, if we allow also the body of the robot, so the full embodiment to change on the base of performance, if we also allow essentially the robot design to change on the base of how well a task is doing, will we arrive on the same type of systems? efforts we have today. That will be actually closing the loop fully from, not only from perception decline, but also the robot design as part of the loop. And I just want to say that there are currently activities along this axis. I was very happily, I think there's a workshop from Emilio Frazzoli in this IROS about computational design of robots, which is very relevant on this question.
I have a question. Yeah, I have a question about the like how to design the model about like what the kind of the mutual dependence. For example, like how important would be, for example, concerning the running control for perception, enhancing the capability of perception, and like how to, for example, switch the role of running control to reach some to aim some as objective or enhance the capability of perception, something like that. If you have any idea or thoughts about it.
Do you mean, if I understood the question correctly, where should we focus on, or when should we switch between the two?
Yeah, maybe the latter one.
So when should we switch?
Yeah.
Yeah, I guess from my perspective, we have to be able to have some sort of understanding of uncertainty and task completion, which the robot itself should have, right? So it should be able to understand, am I progressing into solving a task? Am I understanding properly the dynamics of this problem? Am I deviating? So I think then you can have some sort of objective that can be tracked on a more high level, that can tell you that, okay, now you don't know how to do this task, you need to do something else. Could be that you need to update your representation, could be that you need basically to update, where do you focus, or how do you represent the problem, or it could be also a reasoning issue. So it's actually the reasoning has a point there in all the integration. The question is again, how does it, where does the source of uncertainty comes from? So, and this is, I think, one of the biggest issues that we cannot currently fight for bringing like robots in the real world, even in semi-structured environments in the real world, and not, some warehouse and something where you have humans also being standalone and intervening whenever that's the case. So how do we quantify different sources of uncertainty, and then where are you able to understand when to balance, the different uncertainty levels? Because maybe there is some uncertainty that I don't know what there is behind me. It doesn't matter because you are task specific, doing well, so you can complete the task, for example. So I think that this is one major issue.
Yeah, this is a very interesting example that we were in mind as we were talking about this. I was driving in my home country in India, and the car's wipers were not working and was downpouring. And I was very rash driver by nature, so I just took the car out and had to go somewhere. And the downpouring thing, the wipers were not working, and I somehow managed to, was noticing the headlights of the cars in front, and by all definition, perception was bad, but I was completing the task according to my world model, my own nature, right? So I think it's very much application driven. Like, it depends on the application. If you're in a very simple environment with no one around, and it's indoors, it's perfectly mapped out the environment, maybe you're good with perception. Now so you focus on the navigation algorithms, maybe, right? So I think it's application dependent and task dependent. If you're able to, given the perception capability that you have, or if you're able to complete the task, then that's good enough perception. Then you just focus on improving the task, right? So I would say that, it depends on task and application.
Thank you.
Any more questions? Yes, please.
Thanks for the talk. So I think now there are like mainly two ways for the perception and navigation. One is like to use the HD map and do the effort map to the localization and measuring. Another one is like more like human, we do the segmentation workflow and drivable and do the traffic control. So which one do you think would be like the future of the navigation? And or even maybe there are like even better ways to solve this kind of problem?
Sorry, did you say HD maps and what was the other one?
Yeah, so I think like one way is to use the HD map, the localization and navigation. Another one like use like human and do the based on the the workflow or drivable area, and then we do the navigation. Like two ways. Which one will be like the future?
Not sure I understood the second one. You said like the second one is.
I think the question is high resolution maps over which you can do motion planning and so on forth, and then the other is like more like just the segmentation of. So you get essentially a small patch of the environment. Here you can drive. Here you can drive.
But more like a local view.
No, more hierarchical.
Hierarchical, yeah.
I see. Well, most autonomous driving, they rely on HD maps. Like they use HD maps in order to reach that level of autonomous capability. So I'm not sure. I'm in favor of maps. Like I would require maps in order to because my interest is my main focus is like personally would be on navigation. So I want to make sure that like that I have the perfect perception as much as I can, and I believe I get that from maps rather than hierarchical representations.
I can just give an alternative view, not different views, but I will just propose a different criteria. I think a better way is what is more interesting to each of us, or what maybe I believe that's the applicable approach, is to put the latency as the metric into your question. So every task that you are referring to, building the map, building a dense map, segmenting out the map, not using a map at all, making a reactive policy, each of these has a different latency aspect into it. And in fact, in my opinion, the best way to look at it is that it's a question of latency, a question of horizon. For some longer horizon paths that you can afford the latency, then you can use much more rich representations that include semantics, for example, because you have time to do so and you are planning ahead. And then if you need also to have all the way to the lowest level, the ability for reaction. And then you don't have the time to have latency inducing tasks, such as segmentation, for example, or making a very dense map. And this is where a neural network, which is trained for guaranteed time of inference, and you can also keep it by design if you want short, might allow you to also have a good avoidance alongside tracking your basic trajectory. So a good criteria instead of what me, somebody else, Georgia, anybody else for this year or another year in this community is doing is latency and the horizon of the task. Latency perception and the horizon of planning for control problem.
Cool. I think we have some time for just the last question. Maybe I think we have one last, please.
So my question is about the like the robots should know the agents interaction.
I think we cannot see you very well. Can you? Maybe just bring it closer to your mouth.
Does that work?
Yeah.
So my question is about the reasoning part where the robot should know the intention of the agent, for example, human. So how to get these models, like how to get the human intention or human perspective. For example, if a drone is there and for safety purposes, drone can pass from vision techniques, drone can pass or through like very near to me. Although it does not hurt me, but it kind of scares me. So how to model that personal space of a human so that apart from safety, I have like a total safety kind of thing. And if using deep learning techniques, how to get a correct data for that accurately, because human intentions change very frequently and depends on human theory. So how to gather data and how to get those models. And in last, how to form how to check the results.
Always brave. I can start mostly because I speak fast. I don't push me. So I think it's your problem, right? If you know what behavior you want the drone to have or any other robot, I think that's absolutely doable today. But the more interesting part of your question is that we actually do not necessarily know, right? And when we do this kind of very niche, specific task-driven solutions, we don't account now for all that. So, in my view, for example, if it didn't go really towards you, then this means it was collision free, as I said, right? But it annoyed you, as you said. So then there are two aspects to it. There's an aspect of really good simulation. I think that also has limitations because how good our simulations will have some level of fidelity and they will not include this maybe no more subtle cues like I was annoyed from the noise and so on and so forth. And then the second aspect of it is, should we at some point be able to learn from data? And of course, learning from data will not be at the level of a single agent because simply this one agent will not have the capacity to amount of data and learn capacity of data. But the good thing with robotics is that these are systems we build. So if we were to look at the solution at scale, should we be collecting this data and collecting reactions of that nature? We could have a penalty somewhere in the loop, right? Now, is this something that we'll be able to execute in a lab or in a small initiative? Absolutely not, right? But then, so this requires at some point robotics to work and develop also at scale. So we need industry to work on this level and so on. That's my 2 cents. Georgia.
Yeah, I would agree that you can only learn this by experience. Like when you are a kid, for example, you go and you pull your mother's hair. It's annoying, it doesn't kill you, but it's annoying. But at some point you learn that you should not do it, most likely. So it's only by experience. The question is, what are like the metrics that you develop into understanding that the human got annoyed? Is it that the human expressed it? Is it because we have these models of expressions and so on? But to come to your question, like there are also, apart from safety measures that you can design on a human based, like, I don't know, control barrier functions or, any kind of methodology for planning without like violating safety constraints. There are also the work from social navigation, social human-robot interaction, where they have identified computational models about social norms, for example, about distancing and so on, which is something that we could borrow also from other fields, right? Because people that are doing like social robotics are working with psychologists and so on, and computational psychology, where they try to model things. So if you can, for example, also model computation, create computational models, you could simulate situation, create reward functions, and then keep adding new and more data from real world experience to actually make your behavior better, balance out your reward functions and so on. So I would say that probably it's a mix of things, of deploying some sort of computational behavioral models about humans plus learning by experience.
Yeah, no, like there's very little to add. That's mostly a perfect answer. I think the last part of the question was, what are the challenges and how do you evaluate it? So I can maybe just add a couple of points there. So the main challenge with this is that even in like, as you said, like in social navigation and the social robotics community, the way people are doing it is through a data-driven fashion, where they're collecting data and then trying to learn cost function and reward function. And so your annoyance could be basically a variable in the cost function that could be learned from the data. Now the challenge will come because when you collect a bunch of this data, right? And when you do test by inference, there will always be certain instances which will be out of distribution, and then the model will struggle there. And we have seen these kinds of failure cases, at least in social robot navigation, where if you've learned a model of the cost function, model of the human's risk tolerance or risk preference, and then you deploy it in a different environment, the imitation learning algorithm completely falls apart. So the outer distribution is a fairly terrible beast to slay. So we have to focus on that. And how we evaluate it would basically be that you would deploy these learning models in the downstream tasks, and basically, I guess you would see how they perform. And you there would be some bootstrapping involved, so you'd collect more data and then you reevaluate it, and then there would be a loop that you would keep running.
Okay, so I think maybe that's a good point to stop. I'm sure most of you want to join the welcome reception for a drink. So let's thank our panel for their time. Before you leave, we have the final announcement of the Best Poster Award. So I would like to announce that now. So I hope that Parker Owen is around. Present the poster, yes, please come up. Yeah, great. So Parker presented the poster of multimodal semantic perception using logic inference, and it was selected as the best poster presentation. And that's the award. Yeah, congratulations. Yeah. Thanks for being here. Great. Cool. Thanks everyone for attending the workshop. It was great having you here. And